Good morning, everybody. Welcome to the second day of this EO for Cultural Natural Heritage workshop. We are about to start now the morning section that is about application for preventing and preserving. And now we will give the floor to the first keynote speech. We have today with us Jyoti Osagrar, who is the Deputy Director of the UNESCO World Heritage Center. Good morning, Jyoti, and thanks for your patience. The floor is yours. Thanks.
Good morning. Thank you. Thank you very much. Let me begin to share my presentation. I need a second for it to come up. Okay. I think you should be able to see my screen.
Yes, thanks.
Okay, great. So, good morning to all the distinguished guests. First of all, I would like to express my gratitude to the European Space Agency and the European.
Sorry, we cannot no more hear your voice.
Okay, so we are experiencing some issues this morning. We propose to move to the next presentation in the meantime. We will go back to the UNESCO presentation later on. So I would invite Andrea Cavallini, Preserving Cultural Heritage, AI-driven preventive archaeology through multi-seasonal remote sensing. Thank you.
Good morning, everybody. Thank you. I would like to say thank you to ESA Herzl to hosting this interesting event about Earth observation and cultural heritage. So today I'm going to present something that is called preventive archaeology. It is Smart Dig is a project that the Starion Group is developing together with ESA. So we know that today we have a huge need to preserve what is our cultural heritage. We know there is a huge urgency to preserve because we know that there are many factors that affects and put in danger our cultural heritage, from pollution, also people endangering intentionally or not intentionally our cultural heritage. So we saw also in this context there are many activities on their way in order to preserve and to maintain and to monitor what is the status of our cultural heritage. But we have to preserve everything that we know, but also what we unknown. So what is the unknown heritage? Is everything that is still buried in the ground that we don't see. So how, the main question is how we can preserve something that we don't know where. And if we think also in this area, Rome and Frascati, it's full. Every time that you start to make also a simple building, there is the 100% chance that you are going to find something. So we have in some way think how to preserve everything that is not still discovered. Also because from one side we have to preserve the cultural heritage, but at the same time from people working in the building environment could incur in additional cost because they have to stop the jobs, maybe delays. So it's something that we have to have a real attention. But the main question is how we can preserve, but in general identify something that is not visible. That is the primary question. Let's say in reality it's something that we discovered several years ago because from everything that we can see from the top, it's possible to see something that it's in some way hidden by the ground. So the only way that we have to elevate and how we recognize that there is something buried in the ground, we have several indicators. This is one of typical indicators that is called ground indicators that are like crop marks and ground anomalies that according to the nature of the buried remain and the reaction with the vegetation of the soil moisture, you can see from the top, I think it's more or less all this kind of square and circular structure that in some way hides something that is buried in the ground. At the same time, the presence of some materials under the ground can in some way change the elevation of the ground. And thanks to the shadows or to simply the change of color, we are able to see that is something buried for sure in the ground. So this comes the topic of preventive archaeology, that Just to give you an example, in Italy, but this is true in all the countries, there is a legal obligation that because we have to preserve everything that is bird, before starting any kind of activity, we have to make a preliminary assessment to see if there is something. And if there is something, so I have to build a new house, I have to be 100% sure that there's nothing in the ground. And this requires, let's say, a procedure. So in Italy, there is a very strict procedure that, oops.
So today is only for really passionate people to stay here.
So before starting any kind of activity and job, there is the company that has to make this kind of excavation work have to hire some specialists, they usually archaeologists, that have to make a preventive analysis of the ground to see if there is the chance, because of course some often are some evidence, but there is not the real truth. So let's say the survey on the site is always required, but at least a preliminary assessment to see if there are chances or not to see something. Then today, because there are no actual tools for the archaeologists to make this kind of analysis, they usually go using Google Earth and or Google Maps or whatever to make this kind of visual analysis to see if there is indeed something behind. Then they prepare a report, and then the report is given to the right authority, and then. But this takes time. Of course, also the analysis itself takes time, days, and usually could take also 2 months. That if we think this for every site to be worked and every company, this is a huge delay. So it's important that we are able to find this kind of evidence as soon as possible. At the same time, we have a good need to make this as much as possible accurate. So we saw before in the previous slide that there are many ways, because there are drones. Today, let's say, it's one of the, I would say, could be the best one in terms of resolution. We could have airborne, but all of them have some limits. Because if I think a drone, if the weather is not, it's not in the correct moment, so there is a lot of wind, I cannot make any kind of survey. If I want to cover a huge area, of course it's expensive to go with a drone that also thinking about the autonomy. If I have to make this survey in a systematic way, it's even more expensive. And often the problem is that we are constrained to a moment. So if I want to make this analysis, I hired a professionist, we go with the drone, we make the survey. But what happens if the situation of the terrain is not favorable for the visualization of these remains? And this is just to give an example. These are there are 2 sites with 3 different time instants of the same area. So if the conditions on the ground, on the moisture, on all the elements that in some way gives the evidence of the archaeological remain, maybe that I'm going to do the survey on the time of the first image, I'm going only to waste money. That's the main issue. At the same time, I'm not sure that there is something or not. So there's no way to see if there is something. That's why we are relying a lot on Earth observation. This comes Smart Deep project. That is a project that is developed by Starion and is founded as a part of the ESA Incubate program. So ESA is co-founding this activity together with us, having the support of the Ministry of the Culture. And just to give you really small information, it's a WebGIS application that is meant for professionals that work in the field of preventive archaeology. So most of the times are archaeologists that use Earth observation data. Today, typically optical radars, because they have a different way to detect its buried remains, using AI technology, both for the detection itself of the buried remains, but mainly for enhancement, because we are always dealing with very small features that we struggle also by naked eye to detect. So we have several AI technologies that are meant to enhance and to find also the best ground condition. That's why our analysis is based on multi-temporal analysis. So we are not tied and connected to a single instant, but we are going and looking in the past, finding the best situation of the soil in order to see or to try to exploit if there is something. At the same time, the fact that we are going to see multiple instances in time gives us also a sort of confirmation if what have we seen and detected or meant to be an archaeological remains bird, it really is this, because sometimes there are some tracks on some effects of human behavior, also during the harvesting, that maybe could seems like a crop mark or something that is bad. In reality, if we are able to confirm that this track is always the same during the time in the past years, means that there is a good chance that there is indeed a real archaeology remain. At the same time, we are thinking this project as much as possible oriented to the customer. That means we are working together, and we have several stakeholders that are archaeologists working today in this field. So all the requirements that are coming in this project are gathered from them. At the same time, because we know that usually they work with QGIS because they are going to prepare, at least we know very well in Italy, they are going to prepare this report that is integrated with GIS system that they are using for the preparation of the report. We are also providing a way to directly have an interconnection in order to integrate their system with our results. This is very high level picture just to show. So we have a user that can be either a user that ask the service for just one-shot analysis, or maybe for a more systematic way. So I'm a professional that work daily with all the several companies. So maybe I could go with a machine-to-machine interface using my custom GIS application. Then we have a backend that it's going to handle all the requests. So we are going to deliver take data from different data sources. Today, as a starting point, we are mainly working from Copernicus data. But of course, we have in the plan to use also historical photo from Aerofototeca Nazionale, also from other sensors like LiDAR and so on and so forth. And we are not thinking, of course, this is an application that is meant only for Italian market. We are going to deploy and to develop this to work worldwide because, of course, they say in Italy we have many cultural heritage, but we have many evidence in all the rest of the world. And the fact that we rely on Earth observation data, and so we are not in some way constrained to some local position, we're able to do this kind of detection and monitoring, both on a global scale, but also on a systematic scale. And this is also important, and I'm very close to conclude, also to the fact that today many evidence are quite, let's say, if the conditions of the ground are good, are quite easy to detect. But we saw that some sites have been affected by urban growth. So maybe that if I saw that area 20, 30 years ago, I'm able to see something, but today it's totally hidden by the urban growth. That's why we had also an ongoing discussion with ESA, a Heritage Space Program group, that is hosting all the historical data, all the heritage mission of ESA. So we are able really also, in fact, I'm sorry that the previous, from UNESCO, that she started speaking about Landsat 1 from 1972. So in reality, thanks to the support of a HSP program, we were able to use, in theory, all historical data that could give us better data also to train our AI model, but also to exploit this multi-temporal analysis. At the same time, they are going to provide us a dedicated data set in order just to support our project. So just to conclude, of course, our object is to make this tool as much as possible the main tool to do preventive archaeology. It helps to make any kind of activity that is fast, of course, and non-invasive. So we have to reduce all the times that today are very manual times that are spent during this procedure. We are trying to use as much as possible artificial intelligence and Earth observation data from very long past in order to give as much as possible precision and accuracy, because every nation have a different way to express the cultural heritage, so we have different features to detect. And as I told just before, for us it's a global solution that it's important for the safeguarding of heritage, so the monitoring and the preservation. We are going to make this as much as possible scalable, so we plan to serve starting from Italy and then spreading worldwide. And as I told you, the most important part is that it's built for expert with experts. So we are working closely with the cultural heritage expert in order to make this something that is a really useful tool. That's it. Thank you.
Thank you, Andrea. Is there any questions for Andrea? Thank you.
Thank you.
Okay, so we can move to the next presentation, I think, right, Sabrina? Okay, so we move to the next one. Will be given by Fabienne Castel. Earth observation data to determine the carrying capacity of tourism destinations.
Thank you, Yolanda. Hello everyone. Yeah, so let's start. I will first present myself and my company. So maybe you already saw that yesterday, but I will still say some words here. So we are Murmuration, a private company based in France. Our goal and ambition is to put environmental factors at the center of decision making. And for that, we compute environmental indicators from Earth observation data, mainly Copernicus data, but also other Earth observation data. We mainly focus on the tourism sector. So we have customers on local, regional, and national tourism institutions in charge of managing tourism. And so here I will talk about work we are doing with this institution to manage and to help them manage tourism activities and tourism pressure on environment. Here we have to keep in mind that for tourism institutions, the first objective is to maximize the number of tourists and their spending on the destinations. That is their role, that is their first role. But over the last years, they also noticed that tourism activity can become a problem when it is too important. It puts a lot of pressure on environment and also on destinations in general. So to manage this problem, institutions can, they have different tools at their disposal. They can first lower the communication, for instance, to have less visitations. They can also implement quotas or even close the sites for some specific periods. But the problem today is that these decisions are not really based on actual observations. They are based on qualitative judgments and rather than objective observation. And so here comes the concept of tourism carrying capacity, which is here the idea is to really be able to measure how much tourism how much tourists can come to a destination without pressuring too much their environment. So this concept, it doesn't come from nowhere. It exists in the research field from the 70s. It is mainly based currently on a qualitative approach. That means interviews and surveys with decision makers, with residents, with tourists also to evaluate their satisfaction, for instance. And they are also based on field surveys that are, as always with in-situ measurements, they are one-shots, they are costly, and they do not grasp all the information on a territory. So that's an issue to be addressed here. And and from the research field, we can get the information that usually tourism capacity of a destination is a multi-domain problem. It is related to environment, but also to social and economic factors. So we have to take that into account. So with all that in mind, we are developing, so in collaboration with some tourism institution in France, we are developing a methodology to improve this carrying capacity measurements and to have a methodology based on actual observation. So here, I will not go into all box in this chart. But the idea here is that we will base our methodology on a set of quantitative environmental indicators that will then be modulated with more qualitative factors that can be social or also environmental. But the idea here is really to have, at the basis, a set of quantitative environmental indicators. And here, of course, Copernicus and Earth observation data can help. The concept is to have all these environmental indicators based on Earth observation data. So we will focus on the next slides on the first step of this methodology, which is environmental indicators. So here, the challenge will be to establish capacity thresholds, because that's the goal here. How much tourists can we have on a destination? So how to establish this threshold from Earth observation data? That is really the challenge here. And we will focus on a concrete example after that. But before going to this example, I need to introduce a non-Earth observation data source that we need for the methodology, and that will be tourist attendance. We need here the idea to establish threshold will be to cross-reference Earth observation data with tourism attendance data. And for that, we have different sources that we can use. I'm mentioning here, well, the two main sources that we use. First, it's the FluVision service that is provided, well, it's a commercial service provided by Orange in France, but also in other countries. And it comes from mobile phone networks. It provides tourist tracking statistics based on their mobile phone and how they interact with the mobile phone network. So with that, we have daily statistics of tourist presence. And the other source that we can use is called EcoCounter. So it's basically automated counting systems that are put on pedestrian tracks, and that can count how much people are passing through. This is very local, but very precise. I would say FluVision is less, well, it's more large scale, a little bit less precise, but more large scale. So still, it's very interesting to have this time series of data and cross-reference them with environmental data. So let's go now to a concrete example. And so this is one of the environmental indicators that we will have at the input of the methodology. And this is vegetation trampling. By vegetation trampling, I mean the compression of soil caused by frequent passage of pedestrians or animals. So here we are talking about pedestrians. And it has many impacts on the organic matter in the soil, on the soil structure itself, and it also leads to a reduction of biodiversity. And so here we have an example. Well, this is an extreme example I have here in the picture. It's a festival, well, an event, a music event in France. So a lot of people are coming to a place and they stay for some days, and after they left, there is some trampling effect for sure. So this is a very extreme event. It's less extreme usually when tourists are coming to hike on a place, but still the idea here is to grasp and to measure this impact. So how do we measure this trampling effect? We use Sentinel-2 data. We can also use Planet data for better resolution, but it works very, very well with Sentinel-2 at 10-meter resolution. And what we will do is to calculate NDVI index, so vegetation health index, on trampled areas, so on areas that are close to pedestrian tracks, and compare that with areas that are not visited, that will be used as reference areas. And we will compute NDVI difference, and we will cross-reference this time series of NDVI difference with our tourist attendance data. So here I will show some results on two sites. One, Gavarnie is in south of France, in mountains, in Pyrenean mountains, and Ploumanac is in across the sea in Brittany. So two different sites, but that where a lot of tourists are coming. So here are the results we have when we put attendance data and NDVI difference time series on the same plot. We have some pre-processing steps and data engineering steps to interpolate the vegetation data we have, to smooth them also, to have some discretization. I will not go into a lot of detail on these pre-processing steps, but it allows to establish a link between tourism attendance and vegetation health here. And so as we expected, when we have more tourists, vegetation is impacted. And so once we have established this link, we have to evaluate where do we put the threshold. And for that, we used a breakpoint analysis method to really find what we call breakpoints. That means specific points in the relation where we see that if we had tourists, it will have more impact on the vegetation. And for the two sites we experimented here, we found this threshold here. And well, from this information, we can say with a good confidence that above these numbers, the impact on the vegetation is becoming more important. And so we can provide this information and have this kind of capacity threshold regarding vegetation. So that's the idea for vegetation. We also have the same kind of approach regarding air pollution. So we can have the hypothesis that the more tourists we'll have, the more air pollution we'll have, because tourism activity will generate some displacement, some transports. This is something that, that's the basis hypothesis here. Here we have to keep in mind that it's a bit more complicated than with vegetation, because we cannot establish a link between tourist presence and air quality if we don't put in the equation weather conditions. Basically, if you try to establish the link, if you try to look at the impact of tourists on air pollution on a day where wind is very important, you will just see nothing. So we have to put that in the equation. And that becomes a multivariable regression, which is a bit more complicated. But still, on some destination, we can establish a link with a good confidence. And of course, the relevant destination will be the one where tourism is the main activity. If tourism is diluted into other economic activity, we will not see any link. And so, for some destination, we were able to establish links. So here I'm showing the example in Montpellier in France, across the Mediterranean Sea, which is also a hotspot for tourism. And here we have to keep in mind that as air pollution is also influenced by weather conditions, the result we'll have will be monthly thresholds. Thresholds will not be the same during, in different periods of the year. That's one of the main findings here. And here comes the conclusion. So here, I presented a methodology to establish capacity threshold based on actual observation. That's a work in progress, and we want to, we are considering and we are working on adding other environmental factors. Water resources, for instance, is well, a relevant factor on many different places. Impact on biodiversity also, we want to work on that. It's a bit more challenging to address because we lack reliable observation data for that, but still it's a topic very interesting to address. And maybe, well, one of the main findings we had is to, well, how do we combine the different thresholds on different factors to have a global threshold? And usually, all environmental factors are not limitation for a given destination. Like if we have a city, for instance, will have more air pollution problem, but there are no air pollution problem in the mountains in Gavarnie, for instance, where the limitation will more come from the vegetation. So actually, in our analysis and in our methodology, we are analyzing each factor and keeping only the relevant ones, the one where we can establish a link between tourism attendance and environmental factors. And that's it. Thank you for listening. Do we have time for a question?
For only one question.
Only one. I don't know if we will have one.
No
I have one
questions?
question. I have one. So you were saying that the mobile analytics are a commercial service provided by Orange, is that right?
Yes.
Which kind of data do they provide to you? For example, origin destination matrix. Can you please elaborate a bit more on that?
Yes.
Thanks.
Yeah, first maybe it's a commercial service, but I will answer the other question. Institutions are usually contracting with Orange directly, and they provide the data to us. So it's not part of our service, and that's usually very, very convenient. And what they provide are statistics on a given area, on the tourist presence. So they are able to detect people that are tourists because they are not present in the area during all the year. So they are able to provide statistics on tourists, on residents, also on people that are just going through the area. So they have a lot of different statistics like that. They also are able to cross-reference this information with their customer file, so they can know where does the tourist come from. That is not very interesting for us, but for tourism institution, it's very interesting to know foreign tourists, to know more local. So yeah, there are a lot of information in this data actually, and the main objective of this data is for tourism institution first to evaluate their marketing and evaluate their how they interact with tourists. So we just the usage we are doing with this data is very unusual, I would say. Thank you.
Thank you. So now the next presentation is about analysis of spectral anomalies in multitemporal and multispectral Sentinel-2 data for preventive archaeology, the case study of Telesia Benevento by Antonio Corbo from University La Sapienza in Rome. Thank you.
Thank you. Before I begin, I would like to thank the organizing committee for the opportunity to present this work and Professor Tapete, who supervised the research and provided me valuable advice. The project I am presenting today is titled Analysis of Spectral Anomalies in Multispectral and Multitemporal and Multispectral Sentinel-2 Data for Preventive Archaeology, the case study of Telesia, Benevento, Southern Italy. Introduce a new methodological approach for landscape studies with a particular focus on preventive archaeology, using multispectral Sentinel-2 data acquired between 2017 and 2023. The study area is the lower valley of the Galor River and the ancient Roman city of Telesia Vetere. This area, like many others, is subject to change due to agricultural practices such as deep soil excavation for crop planting, intensive machinery use, and invasive soil processing techniques that compromise the integrity of buried archaeological structures and cause a constant loss of historical data. This area, between the early 1950s and the early 1960s, in unregulated urban expansion and the resulting construction of private buildings contributed to the destruction of many archaeological sites. In the slide, I show before and after of some most important city in the study area. Recently, the construction of a new railway line, which began in 2022, and the establishment of the increasingly large construction sites have led to significant transformation with a strong impact on the entire landscape of the lower Calor Valley. The presence of buried archaeological structure has been confirmed with the rescue archaeological excavation during and before construction. At the same time, there is a phenomenon of neglect of previously excavated sites. The complete lack of attention, sensitivity from the state and local administration has led to the total abandonment of these sites, resulting in uncontrolled and increasingly dense vegetation growth over the years. These factors put the preservation of cultural heritage at risk, necessitating the adoption of new technology to contribute to monitoring and protection of archaeological assets. Remote sensing techniques such as LiDAR, SAR, and multitemporal analysis have proven to be essential tools for creating predictive models for cultural heritage in areas at high archaeological risk. LiDAR, that has been tested in previous studies that I carried out, proved extremely useful in identifying and detecting ancient structure in some areas. You can see the case study of a medieval site of Castel Fenucul's Castle, Torre Palazzo Castle, and Limata Castle. I carried out also a multitemporal analysis based on Sentinel-2 multispectral satellite imagery that has revealed spectral anomalies in vegetation due to the presence of buried archaeological material. Today, I focus on the investigation carried out on the Roman city of Telesia Vetere, northwest of the modern city of Benevento. The methodology used involves the creation of polygons within specific area of interest that correspond to the boundaries of individual cultivated fields. The polygons are used to extract the spectral signature for the Sentinel-2 multispectral imagery. Therefore, it is essential that each polygon falls within a single field characterized by the same type of soil, crop, and cultivation. This approach ensures that all polygons within the field are equally influenced by these three factors, making it possible to attribute any other anomalies in spectral signature to the presence of buried archaeological materials. The polygons created have then been divided into two groups. Group A, which includes the area where previous studies have identified possible buried structures, and Group B, areas where traditional investigation methods have not detected the presence of archaeological materials, constituting reference values to comparison with Group A polygons. Reflectance values have then been extracted from the polygon for each of the individual Sentinel-2 multispectral band. Comparative analysis have been subsequently carried out on the various polygons belonging to the two different groups, aiming to identify possible anomalies in vegetation and soil. The Copernicus data storage provides each Sentinel-2 image as a separate individual band layers. Layers collecting signal in the band B2, B3, B4, and B8 are provided at 10 meter spatial resolution, while B5, B6, B7, and B8A at 20 meter spatial resolution. The analysis of the reflectance graphs of Telesia Vetere allowed hypotheses formulated to explain the spectral signature shape of polygon 5, 10, and 13, located in particular positions. Polygon 10 was created mainly in the lower left corner, or the 20 for 20 meter cell, roughly covering a 10 for 10 meter cell. By importing the RGB preview of the satellite image, we can observe that the 20 for 20 meter cell in question has its upper part in area of interest 1, while the lower part is in area of interest 2. In January 2017, the difference between the two areas of interest was determined by the different type of cultivation. Area of interest 1 visually appeared green, while area of interest 2 was brown. The spectral signature shape of polygon 5, 10, and 13 are characterized by the so-called double hump that you can see in the graph. Can be explained by the way to the values of band B6, B7, B8, and B8A are calculated. The first three, B6, B7, and B8A, have 20 for 20 meter cell, and the reflectance values are determined by the average values of the entire cell. On the other side, the values of the band B8 are determined solely by the average values of the 10 for 10 meter cell, roughly corresponding to the perimeter of the created polygons. In the case of polygon 10, for the October 2017, in the second graphs, the 20 for 20 meter cell includes the vegetation of area interest 1 in its upper section and the absence of vegetation in area of interest 2 in its lower section. Consequently, the double hump in the spectral signature results from the combined influence of the two different sections, the vegetation area of interest 1 raising the values of the 20 for 20 meter bands B6, B7, and B8A, and the vegetation free soil represented by 10 for 10 meter bands, resulting in lower value. This contrast generates a spectral signature with two distinct peaks, reflecting the variation in length cover with the same cell. By the way, the results we obtain show a clear spectral separability between areas enclosed in polygons without archaeological materials and those with archaeological material. Specifically, the spectral signature on polygon 7 in area of interest 2 have lower values than those of polygon 12, where an ancient road passes through. Additionally, polygon 14, which apparently have no archaeological materials, has spectral signature and values similar to those of polygon 12, so it can be hypothesized that archaeological materials may also present in the area enclosed by polygon 14. We can see the same situation also in area of interest 3. As observed in polygon 17 and 18, the reflectance values are lower and comparable to spectral signature of nearby polygon, such as 19 and 20, where no archaeological material is documented. Indeed, for this polygon, 17 and 18, the ancient road centrally crossed the polygons, generating anomalies in the reflectance graphs that show spectral separability, even in absence of crop marks. The various reflectance methods also produced positive results when applied to a tall crop like maize, showing separability between the values of group A polygons compared to group B. Polygons 34 buildings and 38 road have lower reflectance values compared to polygon 39 and 14. Areas where traditional archaeology surveys have not detected anomalies. As we can see in the slide, an excellent spectral separability has been observed, which appears in all the years considered. In conclusion, the integrated use of remote sensing techniques and multispectral analysis has proved to be a promising tool for preventive archaeology in the Lower Calor Valley. The spatial resolution of Sentinel-2 imagery is not meant to perform for archaeology, as equally as commercial very high resolution imagery or aerial photographs do. But the regular provision of cloud-free Sentinel-2 allow for multi-temporal analysis that can show spectral patterns repeating over time, and this be used to distinguish spectral profile and support hypotheses about the presence or absence of archaeological materials. The results obtained open up a new perspective for cultural heritage conservation in areas subject to rapid anthropogenic change. Thank you for attention.
Thank you for the presentation. Do we have questions? No questions, so thank you. We can move to the next presentation. Given by Noemi Zabari, enhancing subsurface analysis of heritage sites with synergy of moon tomography and remote sensing. Thank you.
Hi. Yes, I took my own microphone. I never liked this one. Hi, everyone. I'm Noemi Zabari, and I came here to represent the company that is called Muotech. And in Muotech, we are developing and we are working very hard to develop a technology that is called muon tomography. I come from a different background. I'm an astrophysicist, and I think I need to go here to click the next one, right? I can take it? Perfect. Yes. So very shortly, I will first talk, present you what is muon tomography, then also some of the applications of the muon tomography, what is cosmic radiation, which is exactly what I'm specializing at, and why this technology is possible and how does it work, which I would like to show you the potential of it, the potential that it holds. And then what we are working on right now, which is the reconstruction of the internal structures, archaeological internal structures, and why I'm here and why I came to the conference that is focused on remote sensing, and why do we need, why we are looking for a cooperation in that topic. And then on the end, I will just very shortly show what's the future development and our future plans. Okay, so muon tomography, it's an imaging technique, but also scanning technique, and it's based on the use of cosmic muons, and those muons are coming to us from space. So we are talking here about a space technology for archaeology and artifacts. A couple of applications that already were done. In 2015, for example, muon tomography was used in the monitoring damaged nuclear reactors after the catastrophe in Fukushima. I'm talking here about the big earthquake, and right after there was a tsunami in 2011. And I think many of you or all of you knows what happened in Fukushima. And this method helped to scan and to image reactor without even opening, without touching it. 2017, muon tomography imaged or found a room in the pyramid of Giza. And this is called right now Scan Pyramids Project. 2019, muon tomography was used to image the magma pathways in Mount Etna, and those sequential images that were done using muon tomography, they identified a new vent that in 2021 erupted. 2019, University of Glasgow, they imaged and scanned a huge 600 kilograms concrete block, and they saw reinforcement in it, in that block. And each metal rod was like 8 millimeters thick. And they also, what's funny and very interesting, they also saw corrosion on that metal rods. And 2023, again, pyramid, but this time pyramid in Khufu. They discovered a corridor-shaped structure, and now it's called Scan Pyramids North Face Corridor. And all of that was done, yes, all of that, or most of those discoveries were done using gaseous detectors, what you see right now in the video. Gaseous means that the gas is needed for them. Here it's all argon or helium. And what they do, this one is a spark chamber. What you see right now, it's something that comes to us right now every second, but we can't see it. So what this detector allows you for is to see something invisible. Okay, so just a bit about the cosmic radiation. Cosmic rays are high energy particles that come to us from space, for example, from our sun. It's a solar radiation, but also from different stars. And the events such as supernova explosion, what you see in the picture right now, and from outer space. And that's why scientists are researching it, because they want to know what is in outer space, what is dark energy, what is dark matter. And cosmic radiation, cosmic rays, they allow them to know because they carry information. The particles are mainly consisting of nuclei, mainly protons, but also some particles like helium, nuclear, or electrons. They travel near the speed of light, and they have a huge energies, like tera-electronvolts, which means like hundreds of millions electronvolts. And when they come to us, to our atmosphere, to the upper atmosphere, they collide with particles in the upper atmosphere, and they create, oh, give me a second. That's the video as well. Oh, maybe now. Perfect. Or not? Maybe on the monitor. Okay. Oh, thank you. A magic hand is on it. Doesn't work? Okay. Unfortunate, because it was very good one. It showed how the particle collides with our atmosphere and then create the shower of lower energetic particles. So it was like visualizing what I just said, but I hope you have a good imagination and you can do it by yourself. So the particles that are coming to us, they are called muons, and that's why the name muon tomography. And muons are very similar to electrons, but much heavier, almost 200 times heavier. And that's why they can penetrate through very dense materials. And a great amount of them are coming to our Earth, because it's like 100 particles per meter square per meter. So it's like a continuous data stream. So all the research can be done anywhere in the world. And despite the fact that they are unstable and they decay after around 2 microseconds, because the relativistic effects, because they are traveling fast near the speed of light, they manage to survive and come to us on Earth and underground. We have readings from 3 kilometers underground with still very good flux of the particles. And when they come through the matter, they lose energy by ionization or atomic excitation. And if somebody were doing any research using neutron methods, the difference is that they are not sensitive to strong nuclear interactions. So they don't lose energy on the interactions, on the strong interactions with the atomic nuclei, like protons or neutrons. And in comparison with X-ray, for example, they do not lose energy on effects such as scattering or electromagnetic cascade. So they actually survive more, or they lose energy on ionization rather on strong interactions with electron. And when they go through a matter that has different densities, they lose energy, but also the direction is changes. And that's why we are able to image the internal structure of objects like in X-ray tomography, but with for much higher densities and for much bigger distances. So you can imagine the scanning of buildings, scanning of a structure, of the infrastructure. And that's the two methods that I'm presenting here. It's muon radiography based on muon absorption and muon scattering tomography based on muon scattering. The first one, muon radiography, is very similar to the method of X-ray imaging, and the main equation is Bethe-Bloch, and it describes the relationship between energy loss with couple of different parameters, but it all comes down to loss of energy with relation to density. And it's very good for the big structure. You need only one detection, one detector on one side of the object, of the structure, for example, to have two-dimensional image. And if you want three-dimensional, then you need to create to put more detectors. In regards to muon scattering tomography, it's a bit more complex method, and it's based on phenomenon that is called multiple column scattering. So we are not looking only at the amount of particles that we are getting on the other side, but also at the direction, or how the angle of the direction is changing. And this is suitable for small objects, for example, like sword, like the waves, or something like that. And just because we need detectors on both sides, that they need to be placed in front and behind the object that we are researching. And because of that, with that setup, we can get a full trajectory of those of the particles, and right away we are receiving a 3D density map. Now, what we are doing right now, we are developing a simulation tool. That's what we are focusing, that helps us to model, to optimize, and to analyze the data. And the input are the definition of the detection setup, but also location where the research is done, or where the object is located, which comes to environmental conditions, and potential parameter of objects, potential, because this one is not a must. When it comes to definition of detection setup, we have modeled 3 different detectors, because we noticed that there are different needs right now in the research. We call them Structoscan sensor. This is for the bigger structures, and it's based on those plates of detection. The white, what you see in the Structoscan sensor, you can also open like in the closet on the side, and then you can receive the 3D image of what you are scanning. Then target scan sensor, it's something that the object needs to be placed inside, and it's better for smaller objects, also because you can put, this is based also on these plates of detection. They are on the upper in the upper and down part of the detector. Those are like drawers that you can put in. For a bit bigger objects, you need at least 2 of those drawers on each side. For smaller objects, you need more, up to 4 or 5. And the borehole sensor that came up recently is for a need of underground scanning, and I will talk about it soon a bit more. And what distinguishes those detectors, or what we are doing from the ones that I told you on the beginning, is that we are using so-called scintillating detection. And scintillator, I allowed myself to bring one. It's not so heavy, so why not? Scintillator is a material that emits light when absorb ionization radiation. So when the particle like muon is going through, it emits light. It emits a photon. It's a signal of light. And then what we do, we are using a photomultiplier. We are using actually a silicon photomultiplier to catch that signal and to process it to electronic signal. Inside the detector, it's done this way. Okay. For a borehole sensor, for example, that could be a one use case, or we just drew how to show you, to allow you to imagine how it can be used. We need a borehole. We need a detector to be underground to scan what is above it, but with a very big field of view. It's 170 degrees of field of view. So you see on both sides what you have there. And then it depends on the time of exposure, what resolution you will get. And the goal of mine, why I'm here today, is because we are aiming at so-called target exploration. We need to narrow down specific regions so that we will know where that borehole can be placed or can be done to have to be able to scan the remaining part. And remote sensing comes into play also to overview the size, to optimize location of detector installation, or as a complementary data. We have identified a couple of them, of course. LIDAR comes into place as first, but sitting here today, I already recognized more works, and I came here to invite you for a collaboration and for partnering so that we can do a good together. This is where we are. We are finalizing our simulation tool that I talked a bit earlier. We are building our prototypes. We built small detectors already that we connected. We see the readings. We connected them to our software. And I think the base of the detector, which you see in the upper image, is FPGA. It's for fast processing because it's a tremendous amount of data. Is ready, so the heart of detectors, all of them, is there. Additionally, or simultaneously, we are also working on this intuitive platform because we discovered that we need to widen up our system, as it's not only a specialist that working on it, but it's also a museologist that do not have that knowledge. So we are creating this intuitive and easy to use platform where not only the scans that we do can be held, but also different results, different research using different methods. So that's a couple of screenshots. We are also working to distinguish between materials. Yes, and that's the list, for example, of different research that has been done. Everything can be kept within one platform. And here on that, we are collaborating with CERN as they hold technology that we are using, and the technology is called Rusho for the storaging of data. Thank you so much, and I again invite you to get in touch. I would be glad to talk, and invite you for questions as well if there is time.
Thank you for the presentation, Noemi. Do we have questions for Noemi? No? Yes, one. Me. Who are the users of this kind of applications? You just mentioned the museologists, but...
Yeah, it's actually a quite wide segment of markets because we are starting in archaeology and for museums as well, because part of our team are working at those in this market, but there is also a whole civil engineering. It's also a nuclear safety because we can see uranium in the scans, and also in the application, in the space industry application. So it's good that I'm here in ESA. It's because we are planning to use that technology to first monitor subsystems of space missions, so the EE components, electronic components of the space system, and it's real-time monitoring. It's not like dosimeters that work, that gather data and then you can see how much dose you have. It's a real-time monitoring of cosmic radiation, high-energy cosmic radiation, but also for the future exploration of space, but it will work only in the low orbits to tomograph, to scan the objects in space, because right now already you have projects, startups that I know that they are launching 3D printers, and they are printing materials there, but material is behaving differently in space, and you can like have a constant monitoring of those materials.
Okay, thank you. Okay, so I think we have now a coffee break, 15 minutes, so we reconvene at 10:45, and thank you all. Sorry, we should start with next presentation. If you can take a seat, please. Infatti non lo vedo. Ma era qua. Sì. Oggi è così. So we were able to have all of you here now seated, and we lost the presenter, which was here. Oh, he was here 2 minutes ago. Okay, let's check again. Era qua. Non c'è più. Vado. Okay, so in the meantime, we have the other. We have another present. Do you want to start? Yes. Yes. No. No. Okay, so we start. So this presentation is a keynote speech given by Roberta Onori from SATSEN, Copernicus CESA, Protecting Cultural Heritage Through Satellite Imagery. Please, Roberta. Oh, maybe you need a microphone if you want to say, if you want to. Oh, yeah, okay. Okay, so Juan Escalante will start, okay?
Hello, hello.
Hello, hi.
Thank you, sorry. Well, good morning, everyone. We are now going to present the CESA service. We are coming from the European Union Satellite Center that is located in Madrid. We have been there for more than 30 years. We are doing mainly geointelligence, but we are also the trusted entity for the Copernicus support to EU external and security actions. And basically, we are part of the Copernicus family of services. You know, we have atmosphere, marine, land that was presented here, climate change, security, and emergency. We are part of the security ones, together with EMSA and together with Frontex. So Frontex is dealing with the border monitoring, EMSA with maritime surveillance, and we are dealing with external and security actions. So what are we doing now? We are going to see exactly what are we doing with cultural heritage, but I would like to present a bit more to you the service, and then Roberta, my colleague, Roberta Onori, will present you more concrete cases how we work with cultural heritage. So we have been working with the Commission for more than 20 years, collaborating, and that's why I said the Commission has entrusted SATSEN is the European Union Satellite Center, to implement the CESA service. Before it was called SEA, was Support to External Action, and now it's supposed to external and security actions. And this is a new change, it's a new development that started as of last year with the contribution agreement that was signed with the Commission for the next 3 more years, and then I hope there will be a renewal to continue with this service. What is SESA and what is the scope? So basically, SESA answers to the question of, we enhance situational awareness, okay? We contribute to situational awareness of European, let's say, institutions and member states in security-related, let's say, security-related events, okay? And enhancing situational awareness is a bit of a buzzword, but basically we are answering to the question, what is happening, okay? So what is happening in a certain area, in a security-related event? We are delivering custom-designed geospatial products. Basically, we adapt to the needs of the user, and we tailor-made products in order to benefit the specific requirements of a user. And we assist the user, and we try to enhance this capacity to better prepare, to better respond to crisis. Okay, that's the main idea of SESA. With the new contribution agreement, we started to add more, let's say, to open a bit even more our scope and our, let's say, portfolio of services. And we started to address different policy groups at the beginning of the first SEA, let's say, when we were only support to external action. We were in the G1. G1 is policy group 1, so we were supporting external action of the European Union. But now we have G2 and G3, so more policy groups that we are addressing. So we are also addressing the security challenges of the Union, so security-related events to the Union and to its member states. And we are also adding this monitoring of the implementation of EU law that can be even used within the European Union borders, mainly in the member states, of course, with the green light authorization of a member state. How we develop, the type of services we are developing and we are providing can be somehow grouped in 3 main groups, which are talking about geospatial analysis, where we somehow confirm information, we assess certain area with doing geospatial analysis, and I think cultural heritage definitely falls here. But also we are doing mapping for situational awareness, so a bit of a cartographic product, with this thematic cartographic product that can somehow provide reference maps to understand how you need then to operate in a given territory. And then also support to planning, where we, it's a service, that we deliver in order to support the preparation for a mission or event. These are the application areas that SESA has. We have 11. We are now here for the cultural heritage one, but with the new contribution agreement, we were adding new ones, and also we developed new ones while we were, somehow implementing the contribution agreement. Of course, we are always, user-oriented, so sometimes the users were sometimes giving us the key, a bit of they were shaping somehow how the service could respond. So you can see that it's quite, the variety is quite high. We have 11. We have environmental compliance, cultural heritage, humanitarian aid, trade and economic diplomacy, stability, rule of law, security of citizens. Well, you can see there now the recent, climate security, I think is something is going to be quite important. The SATSEN is going to be most probably the European Union data and analysis hub for climate security. So this is something for the future, and that the SATSEN will be in the lead. How we somehow manage, and SESA has different components. Now we are in a user uptake activity, so we are with users and we are showing the service. And the idea is to promote the service and to do a bit of, exchange with other services and other communities. We need the service provision that I mentioned already. We need to manage the service with our service providers, with our users, but also with the people that are working in SATSEN. And as I mentioned before, we are in constant evolution. We are adding new area of application. We try to adapt the areas to the user requirements. and we try exactly to address whatever developments are coming in this conflicted world. These are a bit of the numbers we have. So far, we have more than 600 activations coming from more than 40 users, and we deliver more than 1,200 products, covering, I would say, you can see there the geographical coverage of CESA is quite broad as well, in more than 90 countries. So basically now I will pass the floor to my colleague Roberta Ortonori, who will present you a bit how we can get actionable data and insights, let's say, from geodata. We are going to see things about site security, transborder trafficking, intentional damage, looting, and conflict-related damage. So thank you from my side, and I pass to Roberta.
Thank you, Juan. Thank you for the opportunity to show a bit of the work we are doing for this specific application area. It's only a part, as Juan explained before. I will use the same slide in a bit different way to make some disclaimer before to start with the technical part. First of all, the satellite cannot answer to all the possible crime in this sector. And here you can see, for example, I don't know how it's work this, but that all the possible crime damages that happen inside something, in a museum, in a place, is not visible from satellite. So the things we can see are, thank you. Well, thank you. So in this case, the satellite cannot provide a lot of information to our user, but also in this case, probably it's not so easy to support the user, so there are some limits. We need to know that there are the limits, we need to play with this limit. But there are some other valuable information we can provide. And we always say to our user that we can provide indicators of something. In any case, the remote sensing is a remote sensing techniques. We need always the support of the people that are working on field, but there are some indicators that at this stage we are considering like fully operative, and we can provide to our user. As Juan said, our community of users, the requests they are addressing to us are usually driven by time and need of confidence level. So the information they need to take action, to decide, to use this information as several time decisions that need to be, that can be an impact. So it's important for us to provide as operative service only indicators that for us are operative enough, and they can be sent or provided with a good enough level of confidence. So these are the two main disclaimers I would like to give as start of this presentation. Then I will go now to several examples quite fast, just to show you these indicators, how we can see these indicators, how we can provide. So you see mainly is the looting, destruction, construction, earth movement that are a bit different for in our classification. I will show an example later. Buried heritage, we spoke a lot about this yesterday and today, and other activity that I will also show. I'm not saying that these are all the support that Earth observation can give to the user. We saw a lot of very good example, good research level, but we are speaking about an operative service. So sometimes we need to answer in hours or days. So it's what is operative, okay? It's not all the possibility of the technology. First example, looting. We have seen several. These are some of the examples we have used in our product. I will not report the places in all the examples, but I can say that there are examples in Europe or examples outside, like Syria, Iraq. And the looting is something that for us is one of the main information the user asks to us. It is also can be also connected with trafficking, so included in a more wide spectrum of information. Sometimes they are asking us to check if there is this type of indicator. Here some other example of looting. You can see the different type of environment, agricultural environment where the looting can happen, or there is one that I can say where is, because this is in Syria, is Ebla. maybe looting with different reasons, some more relate to local crimes, some other more structured crimes. In some cases, the looting can be used to sell the properties and to take fund to finance some other type of activity. So there are several type of different requests the user can ask to us, and the topic is always the cultural heritage, no? So, earthworks. This case, we are also in this case in Syria, and you can see the difference. We make two different classes, earth movement and construction, and in particular for the earth movement, we provide to the user information about something that is destroying in some way the cultural properties, and in some other case, here is a camp, probably a military one, and in that case, we named construction. These classes are explained to our user. In some cases are agreed, and this is close to what we have said yesterday, the discussion to use the same language to understand each other. So this is something in which we are working a lot. So these classes are agreed and are also dynamic because we are changing sometimes the vocabulary, the classification with the user, the specific user that is asking us the request. Going quickly, distraction, this is quite easy. The thing is there or is not there. Also in this case is this was the specific element. Okay, we spoke a lot about this. This I think also is the same area more or less we discussed yesterday in Iraq, Mesopotamia, and there is different type of the Paleo Channel, the evidence of a presence underground of some structure. This is a place in Italy in which you see here is a place that the people can visit, and close to there is with the same C shape something that is not open to the public, and the place is used for agricultural topic. The other nice things or interesting in that area in Iraq, it was the salinity that we also provide this information. It's not only in the area of Mesopotamia, it was not only the presence of the cultural heritage, but also the possible damage of the climate change, in that case, the salinity increasing that were making danger for the specific element. And other activity. This is another class in which we put several different type of element. In this case, we are in Syria. These are all defense wall that have been built because this type of site that are a bit high, the tail can be used also maybe for military purposes, not to see in work environment. So you can see here all the wall present in a site where that potentially can affect the cultural heritage of the area. You can see here this part is here. You can see the damages that happen there. So to finalize, these were only the indicators. In reality, the product we are providing are the combination of this information. I can say that the more interesting part of this type of analysis is the report and the information, the statistics, the multi-temporal analysis. So it's not always, usually we are not working in a single image, but in a period, as we have seen also in other works. So for example, this was an example in which we had to support the security planning of a cultural site to be sure that this can be used by the people, and so it was a monitoring from 2002 to 2020 to check the changes and also to improve a bit the security measure to protect this place. Or this is EBLA, this is the result of the wall monitor we have conducted, in which you can see the different damages we have detected from 2014 to 2020. So usually are work that need in few time the analysis of a lot of information, and this is something that we usually provide to the user also to maybe take measure to prevent, to knowing where is most possible to find looting or the density of the damages that we were detecting. They can use this type of information with the statistics to better understand the situation or to act in some case, to know where is more probable that something can happen. This is one visualization. This is another one. It's always a density map, it maps, to give this type of info. So this was the overview we would like to give to you. And thank you very much for the attention and the opportunity.
Thank you for the presentation. Do we have comments or questions for Roberta and Juan? No? Yes? Miss Mario. Can you just pass him the microphone? Yes, sorry.
Thank you. No, very interesting, and the idea to have a service is quite attractive. But I was a little bit surprised to see that your examples are more on Syria and that. So, is this more to showcase what you could do, or is this official request that you have received?
No. Oh, see, yes. Both. In this case, we select this work we have done, this product we are providing for a user over Syria. And for both reasons, because we have done, the user asked us to make this monitor. It was a multi-temporal, so in that case, we stopped in 2022, the monitor. It was more a study of the history. And and to show also the different type of classes, also because it was one of the main, with this big multi-temporal analysis in which we found a lot of different indicators, because several things happened from 2002 to 2020. So we use this example for both. Every example, as Juan said, the service is only user-driven. I mean, we are not, we are also doing studies and research to improve our service, but the product that I'm showing in this, I have shown today, are always requested by some user.
Okay.
Thank you. So I think we should move to the next presentation now. So I will ask Charlotte Fafet to come on the floor. Thank you. With monitoring and analyzing archaeological destruction in Afghanistan using satellite imagery.
Hello everyone, so my name is Charlotte Fafet. I'm very happy to be here to present today to this conference. So I'm a remote sensing analyst at a company called Econem, which was founded in 2013 and is based in Paris. We are a multidisciplinary team of archaeologists, computer scientists, remote sensor analysts, engineers, and so on, and we're specialized in the digitalization of endangered cultural heritage sites. We've been operating in more than 50 countries where heritage is at risk, and as I just said, our focus initially was on 3D models of cultural heritage sites. So we've done a lot of diagnosis based on photogrammetry, like from capturing those buildings using drones to building the models, and then sometimes like superposing models and so on to conduct multiple analyses depending on the risks or the situation on site. So here are just a couple of examples. And more recently, we've been introducing satellite Earth observation in our work because we figured that it can complement a lot our existing 3D models or the work that is ongoing regarding 3D models and photogrammetry that we're doing. And there are like 4 main points of why this is very complementary. First, it provides like contextual information by providing a larger view of an area. And as we all know, cultural heritage sites are very linked to their surroundings, so it's important to also understand what's going on around those sites to sometimes understand some threats or phenomena at play. Also, satellite Earth observation data provide extensive historical coverage. Someone mentioned earlier the ESA heritage program, which I'm not mentioning here, I'm just mentioning up to 1984 with Landsat 5 because they're a tiny bit easier to play with and to combine with satellites that are still providing data today. There is also the advantage of frequent revisit times because, of course, as I mentioned, we're working with drones, and drones you need to go on site. It is a bit costly, and you can't do that like every like 5 days, like Sentinel-2 provide data for us every 5 days. And also, I wanted to say that, yeah, I just kind of mentioned that EO data enable us to access regions that are affected by disasters and conflicts and where we may not be able to go. So this being said, today I'm going to introduce a work that my team and I have been working on in the past month, if not years, around Afghanistan. We've been focusing on 3 different regions to identify damages linked to looting and anthropogenic destructions. And I think like the previous presentation was a good introduction of some of the phenomena that we have been looking at. And what is interesting around those 3 regions is that we target different aspects of the risk cycle. So the first case that I'm going to cover in northern Afghanistan, we've assessed damages, whereas in southern Afghanistan, we've done more like a preventing analysis to look at potential damage on sites. And then in eastern Afghanistan, we are working on Mes Aynak archaeological site, and there we're doing proper monitoring of the site and its evolution through times. So to begin with, in northern Afghanistan, we've conducted an analysis of looting to support the French archaeological delegation in Afghanistan. They've been operating for many years in Afghanistan, and since 2021, due to the political context, they were not able to be based in Afghanistan anymore. So we decided to support them to work remotely and to be able to still monitor sites there. So they've provided us like a data set of sites in the northern part of Afghanistan, and we've analyzed nearly 2,000 sites to see if those sites had been looted or not. So this was manually generated, but it could act in the future as a training set for automated approaches, and this is something that we're currently working on with academics. So when we started analyzing those sites, what we realized is that there was a new type in the region of looting method that was used. Instead of proceeding to manual looting, which you can see with all the little dots on those images, we noticed that for 136 sites, they have been mechanically destroyed. What we call mechanically destroyed is that we basically used heavy machinery to leveling or to level the site or do some earth moving, and this is a phenomena that we've observed, like I think in the past in Syria and other countries, but not in this region in Afghanistan. The other thing is satellite images were very useful to try to date some looting activities. Even though to conduct this work we needed access to very high resolution images. And so there is like limited images in the archives, especially on those regions. So sometimes it was difficult to properly date the looting activities. So we had like an example before of one site. This is an example of a first site, which was first manually looted, as we can see on this image provided by Maxar in November 2013. And then we see that they use heavy machinery to what we say like mechanically loot the site. Though it was very interesting to figure this phenomena, it's very difficult to interpret because we often say, oh yes, EO is super nice because it's an objective way to look at what is happening on the ground, which is true, but sometimes it's difficult to know why is this happening. And for this, it's useful to talk with different stakeholders having different backgrounds, but still when you don't have access to the country, it's obviously like difficult to understand who is doing this type of looting and why they're proceeding this way, and we don't want to make like too much hypothesis, but something we noticed when we were doing this research is that in the same region they were building a canal, the Koch-Tepa Canal, and we thought maybe there is a link between the construction of this canal and looting activities. Again, I prefer to say this is just an hypothesis. We have no proof that there is a real link between the two. But what was interesting is that the Koch-Tepa Canal started. The project was revived in 2018, and to date there are 204 kilometers of canal that have been constructed. And when we look at the periods of looting activities and the periods of kilometers of canal built, they kind of they're quite correlated, because it looks, the thing that supports our hypothesis is that the heavy machinery could have happened to arrive in northern Afghanistan from 2018 on, and that, we observed that on periods where the canal was not built, there was a bit of looting and so on. But one thing that makes us doubt about this link between the two is that we have the proof by looking at the Sentinel-2 images from January 2024, that they actually avoided one site. So there is, I need to grab this correctly. There is one archaeological site here, and basically this site is much bigger. You see the border here. And they did a deviation of the canal from here. That was the original markage of the canal, and they deviated here north to the site to avoid this site and basically to provide this site. So it looks like on some sites, or at least on this one, they try to preserve cultural heritage. So that's why we can't establish a proper link between this construction of canal and the looting activities that the region experienced. A second project that we worked on that I mentioned earlier was in southern Afghanistan. Basically, we decided to look at other big projects, construction projects happening in Afghanistan, and to see what was the consideration of cultural heritage preservation in those projects. And this was conducted in partnership with the Endangered Archaeological in the Middle East and North Africa team led by the Oxford University. And we focused on the northern part of the southern part of the Tapi gas pipeline. So the Tapi gas pipeline is a pipeline project that is crossing 4 countries: Turkmenistan, Afghanistan, Pakistan, and India. And it started in 2015, to be built in 2015 in Turkmenistan. And we wanted, so with this team at Oxford, to conduct a preventive analysis to basically identify sites that could be affected by the construction of this pipeline. And we identified 433 heritage sites in the pilot phases, and 75 sites were within a 50-meter buffer zones around the pipeline. In order to have a bit of an impact with this research, we communicated our results to the Asian Development Bank, which is one of the funders of the Tapi Pipeline project, and also with the Afghan Institute of Archaeology. So just to briefly illustrate sites that we've identified, there is, for example, ancient canals called kanats that you can see here, and this mark shows the pipeline that would be crossing it. We also have monts and tombs or cemeteries in this area. And finally, I want to quickly introduce another project, which is the monitoring of Mes Aynak archaeological site. So Mes Aynak was discovered in the 60s, and it's used to serve as a mining site from the 1st century before Christ to the 7th century after Christ. And it was an area inhabited by Buddhist monks during this period. And we've been working in this area. So we've been working in this area since 2010 after mining operations started to be renewed in the region in 2008. But also, so another threat that is affecting the site are looting activities that have been observed since 1970s. And there are evidences on that on satellite images, as well as documentation compiled by archaeologists. So the work that we've been doing since 2010, even though the site was monitored since 2008, is mostly photogrammetry centered. We've been doing an initial survey, so flying a drone and building a 3D model of the site in 2010, and then we did follow-up visit in 2011, 12, 13, 15, and 2022. We've also conducted capacity building in the region, mostly only on the use of drones and on photogrammetry. And so the way we've used our models to monitor the sites is by basically like generating a digital elevation models out of those different surveys and overlaying the DEMs to visualize and measure changes. And it was helping us to characterize changes such as like the new archaeological surveys on the site, but also new lootings. We also were unable to see like areas that were eroded, as well as the displacement of excavated materials. Here, satellite EO again became something that was very useful. First of all, to see what happened before the first time we went in the field in 2010. But also to know the conditions during the years we could not access the sites. And basically, the last 2 years, we haven't been able to return to Messinac. So we've also used like satellite EO to try to see what was the evolution, because there is still like archaeological surveys going on and potential looting activities and so on. And I forgot to mention, but this is also led in partnership with the French delegation that I mentioned previously. One thing we've been doing is to develop a visualization tool that allows to monitor the spatial and temporal evolution of the sites. And we've been combining in this tool 3D models and satellite images so that we can really like use those data together to get the most out of both, basically. And as I mentioned, like to monitor also like changes during the time we could not access the site. And looking forward, so our future perspective is basically a bit like linked to the last project that I mentioned. We really want to continue working on the complementary of 3D models and satellite EO, because we think that the two together can be very powerful. We are currently like working on a system, an online system, to alert on emerging and ongoing risks that could potentially affect cultural heritage sites. And as I just mentioned, and as I just showed as well, we are also working on this visualization platform, and where we want to include more of EO analytic tools as well for analyzing ongoing and slow-onset risks. And one of our main goals is reporting and communication. So something, for example, we've done with the example of the Tapi pipeline, because we think that it's important to produce all this data and all this information, but most importantly, it's crucial to communicate with stakeholders that will be able to take decisions on the ground for protecting and preserving cultural heritage sites. And this is the end of my presentation. Thank you for listening. And if you have any questions, don't hesitate to ask now or after.
Questions? No questions? Then thank you, Charlotte.
Thank you. So the next speaker is Giulio Poggi from Istituto Italiano di Tecnologia. He will present an ESAI open call funded project Alceo. Thank you, Giulio.
Okay. Good morning, everybody, and thank you for the introduction. Today I'm presenting the result of the Alceo project conducted in partnership with ESA. The project was funded by the European Space Agency, and the aims of the project are to analyzing the looting phenomenon through Earth observation data, and to automate this analysis of looting on endangered archaeological sites. This automation will be part of a proof of concept for an AI-based platform to counter looting. So the original idea was to develop an AI-based solution for counter looting, in which the detection part would be the main component. The system works so that every newly acquired images is processed by a deep learning model, which automatically detect looting against a data set of images and acknowledged looted activities, looted pits, and detecting the presence of newly appearing looting, send an early warning signal to law enforcement agency for acting and counter immediately the risk. We worked on several case studies. Most important were selected from Middle East, North Africa region, Dura Europos in Syria, EBLA, case studies which already you saw before in the previous presentations, and then as one in Egypt. We also accounted for case studies in Mediterranean area, including Cerveteri and Arpinova from Italy, in order to evaluate different geographical settings and different environmental conditions. So we started by analyzing the images and building the data set. We needed very high resolution images, so we relied on contributing missions for that purpose, and we got some images from Pleiades, QuickBird, WorldView 2, and other, GeoEye, I think. And we got at least 2 images from temporal series, and then you will see why we got these 2 combination of images. And we started annotating the images by manually labeling looting bits on the image. And you can see on the 3rd column how many features we detected for each site and for each temporal moment. Building a data set of about 6,300 looting traces. We conducted the labeling manually on ArcGIS, so we were drawing polygons for looted pits, and we also decided to provide some attributes which would be useful for the machine learning modeling and also for analyzing looting phenomenon with spatial analysis and other statistical methods. We, in particular, decided to try to classify the dimension of the looting pits, whether this was possible to do that, based on mostly on the shape. And also we provided the accuracy, trying to give some sort of reliability to the interpretation, but the problem with that is that the reliability mostly depends on the condition of the looting pits. So if it was fresh new looting pits, probably is more visible than a looting pit that has been abandoned by several years. And also it depends on the quality of the image we are analyzing. So some images have better quality for the specific regions. So that is a parameter that has to be treated carefully. before building a machine learning model, we wanted to analyze what's happening. So we, in the remote sensing images, so we are trying to understand our case studies and how the looting phenomenon appear in those case studies. So about the intensity, we've seen that intensity is much different across the different cases. We have a sparse looting intervatory. In this image we have just 49 bits. We have a clustered looting in S1, which has we can detect clusters and then sparse points. And we have a dense looting over a large area in Dura Europus. Also, the dimension of the pits may indicate that different excavation techniques were applied in different contexts. And about the temporal analysis, we've seen that the looting pits disappear. So especially in arid environments and sandy environments, they get filled by sand, or pits can be redigged. So we have pits that got enlarged during time because probably they were richer than other excavations. So in order to model all these changes, we decided to tackle the problem as a change detection problem. So comparing a sequence of two images and detect the specific changes between these acquisitions in order to account for variation on existing pits over time. The model we selected for this purpose is a Siamese network. The network was trained end-to-end from scratch on our data, so we didn't use pre-trained weight from other sources. And the model works so there is an input 1 that is our time 0, and the new image we want to see whether new looting pits have appeared is the input 2. In the encoder part, the model analyzes separately the two images, extracting the relevant features and combining those features. The combination of the features means that there is a subtraction for the features and the absolute values is computed between this difference. And those information are passed to skip connection to the decoding part. In the decoding part, the network tries to identify where the new pixel that in which the change has occurred in the new image. We had a model to manage data sets, so means we have to prepare the images for train the machine learning model, and we divided the images into tiles, 256 pixels by side, and then we decided to perform a geographical split between training and validation in order to account for spatial autocorrelation. Otherwise, we have biased performance if we sample randomly because of the proximity leads to similarity in geography. So with the split, we also accounted for other problems. That is the unbalanced. We had an unbalanced data because the pits were concentrated in specific portions of the images. And if we wanted to account for a buffer area, in which we may expect to have looting because sites are large, we result in having most of the tiles empty. And this is a problem when you train the model because you need to create batches, so small packages that goes into the memory. And if all those patches are empty, the model doesn't learn anything. So providing the weights, we were able to oversampling on the tiles with events, which are tiles in which there is looting. And in order to achieve a 50% of probability of extracting tiles with events. In this way, we could balance this unbalanced problem. And also, we use the loss function that is the focal loss, in which we teach the model to learn the most from tiles with a few examples and not tiles with a lot of examples. And then some data augmentation techniques to improve generalization capabilities. Those are the results of the performance. These are standard metrics for IOU for segmentation. So it's the intersection of the masks of the prediction against of the predicted mask and the ground truth mask against the union of the mask, and precision and recall. And those metrics are computed for each site. We can see that in MENA region, Aswan, Dura Europos, and Ebla, we got better performance because of the number of the features. We could train on more labels, but also because the environment is easier compared to the Mediterranean region because of the agricultural fields. Vegetation makes more difficult to detect looting pits. In a trade-off between precision and recall, we wanted to highlight the recall values because it means that we are not missing any candidate. I mean, when you have some doubt, it's important to get the doubt, even if that leads to false positive. But in this case, we are not missing any important event. With this performance, we can now test on new images, so we can add images to the time series, and so we can have new inference of newly appeared pits on new images. That was the purpose of the network, and then we conducted a ground truth campaign to verify the results of these new inference. So in Aswan, we had a small survey that we were able to verify the labels on which we trained the model, plus the new looting pits appeared in a recent image we could analyze with the method. And from 129 features, we had 20 false positives from the data set. And this step is fundamental because adjusting this information, we could retrain the model again to get better performance. So this is advisable for every machine learning model as much as the possibility allows for, because we know that these places are very difficult to access. So it's not always possible to do this kind of model refinement. We share the code for the model and the data management part, and the model we used for this task. And then in the future perspective, we got a project extension in which we will improve the data management system. So our goal is to have a smoother integration between the data that archaeologists label on a GIS system. In this case, we are trying to use QGIS through the development of plugin, and how this data get into the modeling part, because these steps are often too much separated that it's difficult to have a smooth integration between the two phases. And also we will improve over the detection methods in order to have to reduce the number of labeled images needed to train this method, because so far we labeled a lot of images, a lot of data, and we will try to reduce the time we spend on labeling by getting ideas from the model itself. So the model will provide us information that he thinks it's useful to train the model. So in this assisted version of this training, we will try to reduce the number of labels. Thank you for your attention.
Thank you, Giulio. Questions? There is one.
Thank you so much for the very interesting presentation. I've got just two quick questions. One, your data set is mainly based on optical data, very high resolution data. So I was wondering if you also evaluated the fact to involve the use of radar data, and the fact that because you are using very high resolution data, okay, you are speaking about proof of concept, but thinking about on an operational point of view, the system relying on very high resolution data, so a lower releasing interval, if this could affect or not the fact of having a very, as close as possible, near real-time alerting system.
Okay, start with the first question.
Thank you.
We thought about the radar data, but with the radar data, if we use Sentinel-1, we have a problem of resolution. I've seen some works that use Sentinel-1 to detect looting. In some specific cases, it's possible, although it's not as accurate as we may expect to have in optical imagery. We are working so far in environments with no vegetation, so optical imagery probably at the moment is the best solution for this task. About the second question, about the data availability, that would be, yes, of course, an issue unless we have agreements with a commercial partner, or obtaining a very high resolution can be one of the challenges. So we hope that we will get this resolution soon free. Otherwise, we have to do some trade-off between the number of images and the periods we want to, on which basis we want to monitor this, the phenomenon. According also to previous experience, we know that changes occurred in specific time intervals or after political events, social changes. So we know that the risk is higher, and we can maybe intensify the monitoring during those periods, probably.
Thank you.
Thank you, Giulio. Now we have an online presentation from Line Dudenoffen from Hensoldt, and she will present an ESA Global Development Assistance project called Fragility, Conflict and Security, and specifically about the use of Earth observation and open source intelligence for land and cultural grabbing. Good morning,
Thank you so
Lynn.
much. Good morning. I'm very happy to be here, even if it's only for a brief amount of time and remotely. Thank you so much for having me. And yeah, so you've kind of already said it, but I'm just going to reintroduce the project, which was funded by the European Space Agency as well, and had several use cases. And we in particular focused on use case 4, namely Ukraine land and conflict, in a consortium with other companies such as Janes, Aegeos, Vito, and DLR. And I myself lead the Intel desk at Hensoldt Analytics. So I'm an analyst by trade. I come from a background of the criminal police. And we at Hensoldt Analytics work in the realm of open source information and intelligence. So we collect big data that is openly available, and the system where we query and store that data is AI enabled and supported. And this is what I'm going to talk about a bit more in a second as well. So the project itself, or the use case itself, in terms of the details, the end user was an international organization, the team already mentioned, and the objective here was that the end user would like to understand how land tenure security was affected in this ongoing conflict, and particularly the risk of land grabbing. Now here I have to add that we focused on systematic land grabs, so not the obviously ongoing opportunistic looting that is always taking place in an active combat zone. And we wanted to ideally establish, how much of the urban environment was damaged and destroyed, how that affected, or how many people in percentages and numbers were affected via Earth observation data. And then we wanted to establish what was looted. Was it property documents? Was it artworks and museums that were looted on a systematic basis, or something else? And by whom? So which military unit was active in the region at a given point in time, just to establish some criteria for future risks, ideally. So why did the end user want that information? They wanted that information to implement land administration and management initiatives, both during as well as during the post-conflict reconstruction that obviously is yet to take place because the conflict has not concluded. Now, These were our areas of interest, very broadly here, very high level. But we focused on the southern axis, east and southeast, and then Kharkiv. Those were identified by the end user predominantly, as well as a preliminary open source intelligence research. So to give you a bit of an overview over the process and the workflow that we used. So like I said, we focused on open source information and intelligence. Information always has to be verified, or else it is just information and stays information. It won't be intelligence unless it is evaluated and verified. So we focused on the monitoring and mapping of incidents of systematic looting at a large scale over several monitoring iterations. Janes then complemented what we did very well, or the other way around. We complemented each other very well because they focused on events and troop monitoring. So that included, you know, the actual conflict development and the whereabouts of military units in Ukraine, Russian military units in Ukraine. So that allowed us, due to the temporal overlap, to assess when systematic looting was mentioned in open source media, for example, on Telegram, which military unit was likely responsible for this systematic land grab or looting. Now, that obviously adds an element of soft attribution of responsibility, which then really turns the whole analysis into intelligence. On the Earth observation side, we had DLR, Aegis, and Vitoy, who all did different things that also complemented each other very well. So Aegis focused on the damage proxy maps, nightlight and fire monitoring, and Vito focused on the harvest monitoring in different regions, and the DLR focused on the pre-war population assessment, as well as the population assessment and damage, the population assessment during the conflict that was based on the damage proxy map. So how many people and percentages and numbers were affected by the damage per building block. So the final product then was a rather extensive and comprehensive report, as well as an interactive proof of concept dashboard. So I'm going to show some further screenshots of that later. So we essentially brought it all on a map, all of our data, to really see the overlap and how it all came together. And we had 3 monitoring iterations, after which the project or the monitoring concluded. And this, just in a different kind of visualization, is how we monitored, how we brought all of our data together. Like I said, on the EOS side, we had different types of data that led to the assessment of people affected by the damage. On the OSINT data, we had events and actors, mentions of multilingual keywords, such as in Russian, Ukrainian, English. We also aggregated mentions of looting and land grabbing and synonyms in Ukrainian, so that we could see per region that we were monitoring whether there was an increase in mentions, for example, of mentions of artworks and looting. You know, so this is then when you have an increase in the aggregate trend data, you can dive down, look behind the data, and run your qualitative analysis, where you can then see what actually happened. So we found that there was a significant increase in mentions of systematic grabs, which makes sense given that it's an active combat zone, or was at the time and still is to an extent. We identified the types of grabs. So was it systematic? Was it opportunistic? And due to the combination of the data of events and actors, as well as our data, that I just mentioned, we were then able to assess which actors were actually active in the region when the grab occurred. This was all logged and stored. And just to give you a bit of an example of what such a table then can look like, this is still high level. There were many more detailed ones, and even here I had to, as you can see, blow out some of the information, namely which Russian units were active in the region when these systematic lootings occurred. And we can see here that we have the systematic looting of artworks mentioned in Mariupol in particular, whereas in Melitopol, for example, what we found is that mostly natural resources were looted systematically and transported away. But in Mariupol, there was extensive looting and systematic looting of museums and artworks. I'm going to show you some qualitative data in a second as well. And then in around Kharkiv, especially at the end of our monitoring period, due to the conflict developments, we had predominantly opportunistic looting, so looting that we didn't include in our monitoring really. When the Russian units were withdrawing, they took a lot of electronic equipment as well as grain. Now, we then had the damage assessment, nightlights and wildfire assessment that I already mentioned. And based on the damage proxy maps that were developed by eGeos, DLR were then able to assess in numbers and percentages how many people were affected in the urban environment that we were monitoring. And if we're looking at a prior monitoring, the prior monitoring iteration, we can see here, you know, in Mariupol, artworks and artifacts were looted, same in Kherson, and then again in Mariupol. So this really happened on a regular basis. It was one of the most common and most prevalent systematic grabs that occurred during all three monitoring periods, where essentially almost every museum was looted systematically and completely emptied. The other most common grab that occurred was the systematic grab of property documents, because in Ukraine, especially in rural areas, much of the property registry is not digitalized, meaning that if Russian military units would collect documents from the town hall or council house or wherever they were stored, and then actually go around to the residents' housing and forcibly take the documents from their house, there was no further evidence that this house or these properties ever belonged to anyone else but now the Russian units. So those were the two most common types of systematic grabs that we identified. And again, here the actors are blurred out, but there was a soft attribution possible due to the monitoring carried out by Janes of when Russian military units were active in the region. And here we can see the looting of or qualitative evidence, you know, the evidence behind all the data aggregation of the systematic looting of cultural heritage. And we can see here the art museum on the top left-hand side, art museum in Mariupol. This is just one of the screenshots of data that was found on Telegram predominantly, as well as back then still Twitter as well, but we focused heavily on Ukrainian Telegram channels, as well as here we can see the situation in the Kherson Art Museum as well. What we can see here is the advertisement of artworks that were looted from Mariupol and then taken to Donetsk, and they're advertised for sale. And we can see here also an example of the trend aggregation, where we monitored, in this case, and for this trend graph, the situation in Mariupol. And we had mentions of looting increase, mentions of land grabbing, and mentions of rape. This is the green trend line here, around about at the same time, and found that the mentions of all three usually go hand in hand in all of our areas of interest. Now, where does AI come in helpful or handy in when you have a wealth of data, such as all of these qualitative results? These are really just examples. We found it quite helpful to run the object recognition algorithms, meaning that certain, you know, artworks or pictures or images could be identified first by the algorithm and then further assessed qualitatively by our analysts. Now, just looking at the time, I don't have many slides left anyway, but this is an example of how we brought it all on the map. The proof of concept information interface that I mentioned earlier, we can see here very clearly the wildfire monitoring that was carried out by EGEOS. Then we have the types of troops that were active in the region at a certain point in time, and we have the number of mentions. Those are the little turquoise squares here. The number of mentions of looting in Ukrainian in a given area at a certain point of time. And obviously, if you animate this over a time series, you get quite a nice picture of what was happening where and when. Zooming in this case here on Bakhmut, before or around the time it was taken by Russian forces, we can see quite a bit of paramilitary troops present. We can see 466 mentions of looting. And here we have 13 mentions of looting at this particular point in time. Obviously, that changes near real time, depending on how frequently you can ingest the data. And as we know now, obviously the Wagner Group was heavily present around Bakhmut at this point in time, and that's why we have lots of paramilitary troops present. Just looking at the damage proxy maps, we can see here the data submitted or the analysis carried out by EGEOS. We can see here first the percentage damage area in the urban environment, which obviously was important for us to assess. And we can then here see the overlay by DLR, where then they assess the population affected per building block. And lastly, a little less relevant for this particular occasion, but I still wanted to mention it. Vito assessed the harvest, the number of times fields were harvested over a given period of time. And this is just an example of an area of interest. But you can see that over time, we already have like many more fields that weren't harvested anymore. Anyway, I have reached the end of my presentation, and I thank you very much for your attention. And if you have any questions, feel free to ask them now.
Thank you very much, Lynn. Questions? Thanks again, Lynn.
No problem. Thank you for having me.
Okay, so we concluded this session for this morning. I will just give you some information that maybe you already know, but so in about 10 minutes we will leave from here and we will have a visit to the FEE experience. So we'll be divided into two groups. All of us, we have to go to this visit all together. And this is a good occasion for you to have a bit more closer idea about the space agency. And soon after we will have the lunch. And we have in the afternoon the last session about the new techniques for the workshop. And after the session of the afternoon, we will conclude with some recommendations and general information for you and for the next events that we plan to have. So now I think in, 5-10 minutes we are leaving from here. And thank you. Okay, so I think we can start with this new session about the new techniques. And I will welcome Arianna Travaglia from l'Istituto Italiano di Tecnologia for a keynote speech. Please, Arianna, the floor is yours.
Thank you very much. And it's my honor to start the final session of these 2 very interesting days. And I will do it with a keynote, which is a conversation with you about archaeology and Earth observation data in the era of AI. And this comes from the experience of my center, the Center for Cultural Heritage Technology. You have heard some of the presentations yesterday and this morning. One more will be included in this session. And it comes from several years. I was saying the collaborations with between archaeologists, computer scientists, specialists of AI, and other experts in order to bring this new era of AI in archaeology and cultural heritage. So in the past, I would say 10 years, maybe would be probably more correct to minimize it a little bit, speaking about the realistic results. But in the past years, we have seen a real substantial increase in the Earth observation missions and a growing volume as a consequence of data acquisitions. The Copernicus data space ecosystem is currently hosting something around 35 petabytes of Earth observation data. This is data from last year. By now, it's probably even bigger. And as of September 2021, the Earth Data Cloud, the NASA cloud-based archive of Earth observations, had something around 60 petabytes of data that are currently estimated to be around 150 petabytes, which are going to become 250 petabytes by 2025. What does this tell us? Well, this tells us that we have a huge amount of data at our disposal. This number of data is becoming immense, and it's making absolutely impractical for us to manage and analyze data in the way we used to. And we all know that the value of the data hinges on our ability to really analyze it and extract relevant information, because that's what we need, the information we can extract from them. So these also clearly affect also the field of archaeology and cultural heritage protection, which is the topic of our conversation today. And the obvious solution as far as managing this data deluge is AI, not only clearly in the field of archaeology and cultural heritage, but also in the, more generically in all the field of Earth observation. So we have seen several examples yesterday, some more today, about how artificial intelligence is being used within archaeology and cultural heritage, and the way in which it is revolutionizing the way in which we process and analyze this data. So of the AI can be utilized in several different ways. It can be used on Earth observation with different applications, from subsoil feature detection to monitoring of cultural heritage. And also it can be used in several different stages of remote sensing data lifecycle. But there are 2 stages in which AI is becoming particularly important for archaeology and cultural heritage conservation and protection and monitoring. So the 2 phases are during the pre-processing phase. So during the pre-processing phase, we can optimize the Earth observation products that are intended for analysis using AI and using approaches for example, for atmospheric correction, denoising, and pan sharpening. The second phase in which we can use AI for heritage is in the phase of the analysis of this data. In this phase, AI can reduce the processing time and reduces the need that we have for human resources. And as a consequence, this also enables us to handle large volumes of data in a very efficient way, a more efficient way that we could with conventional methods. And this helps, as a consequence, also to manage the complexity of this data, because we have been speaking today and yesterday about very different type of Earth observation data, ranging from radar to multispectral. There is hyperspectral as well. There will be LiDAR in the future. So we have a really different type of data that can be analyzed using AI, and in a way that we could not do using conventional methods. As far as using AI for data processing, AI can really significantly enhance the process of image improvement by automating those procedures that are normally very lengthy and complex. And it can do it using the data that are contained in the same image. For example, we can pan sharpen. We can use pan sharpening techniques to enhance the spatial resolution of hyperspectral imaging while preserving the spectral information. There are already, you might think, a lot of methods to do it, but they are normally, the ways that are normally used now are based on data derived from other data external to the data we are analyzing, data that have a bit better resolution than the one we are using. Well, AI avoids to look outside for better data to pan sharpen our data, and can be done with the image itself. So this advancement opens up exciting opportunities, particularly, for example, in the field of hyperspectral data. As we know, and we have heard also, hyperspectral data provide information across a very broad range of spectral bands, and can offer us very valuable information as far as vegetation, soil composition, other environmental factors. These capabilities we know also are extremely useful in archaeology and cultural heritage protection. It's enough to mention our ability to process data about vegetation and looking at biomass of vegetation and using them as a proxy to identify heritage that is still subsoil, something that many other type of EO products are not able to give us. So by applying AI, we can enrich this and process hyperspectral data, and as a consequence, we can also unlock our ability to detect and analyze our data for looking for subsoil features or looking for information about the state of certain cultural heritage sites. From the point of view of the analysis, automating the analysis of images can leverage different approaches depending on what are our goals, what we are trying to achieve, and the outcomes that we want to achieve. For example, object detection and semantic segmentation methods are some of the most used for detection of subsoil archaeological sites. And these are, broadly speaking, the most commonly used so far in all the attempts, which are not that many, I must say, but in the existing attempts of using AI for subsoil features detection. These object detection and semantic segmentation have been the approaches mostly used because they can effectively help us to identify and localize specific objects in the images. Change detection, instead, is another key approach that can be used, and it can be used to highlight environmental changes. So like changes in vegetation, changes in the land use, or even to highlight the happening of natural disaster. And for this reason, change detection is very used for monitoring, because while we monitor something, we want to make sure that we are able to identify immediately something is happening and changing on this site. So using approaches of AI based on change detection is extremely useful. And again, we can do it in a very efficient way, dealing with a much larger number of data that we can do using conventional approaches. Is it so easy then? No, it's not. At the moment, everybody working in AI applied to EU data for archaeology and cultural heritage knows that challenges and are more than advantages. We shouldn't minimize this. We are still in front of many, many challenges, and this will continue in the next years. So we cannot expect that this is going to go away very quickly, especially if we don't do something. So speaking about these challenges, well, the biggest problem that we have, even before starting to approach the design of an AI algorithm or of a model that can support us for detection or monitoring, we have a huge problem with creating training data set. Training data set are the fuel of our algorithms. Without them, we cannot do pretty much a lot. Training data set are needed, are labeled data that are needed for the model to really be able to understand what it has to do. So labeling data is a very, very time-consuming activity, and that's why there are so little training data set for archaeology and cultural heritage. And we can try to use, in these cases, data sets that have been created from other domains. Actually, we have plenty of data sets with cats and dogs and cars and motorcycles, but it's not effective for us working in remote sensing to use that type of data set. They do not work well with remote sensing. So we need to work more on creating training data set for the future. This has to be one of our priorities in order to create better AI models. And we need to create a data set that have some specificity, that are specific for remote sensing and not limited in scope like other data sets that are available. And there is also a necessity for training data sets that are diverse and they are representative because they have to account for the various geographic regions that we have in the world and that we analyze, for the seasonal variation, for the very different sensor type that exist, the environmental conditions. So we really need training data sets that are not only for remote sensing, but are specifically for cultural heritage and archaeology. And one very important thing also is that a reliable data set of this type requires the expertise of the domain experts, which means archaeologists skilled in photo interpretation that can correctly and efficiently label this data in a way that can become really useful for our discipline. Otherwise, we are not moving much. Speaking about challenges and looking at computational aspects of these challenges, one other very important problem is that not much information is currently available about the functioning of certain AI models. So we have the so-called black boxes. And black boxes models pose a significant challenge in the field of artificial intelligence, as they make it difficult for us to understand how the reasoning of AI, this prediction that we get from AI, we don't understand where they come from. And this sort of lack of transparency can lead really to skepticism about the reliability of this AI system, especially from us as scientists, because if we don't see what is the rationale behind certain decisions taken by AI, we are not sure that AI has been able to do the work that we have done manually in conventional way for so many years. If you think about remote sensing and photo interpretation, well, there is a history of over 100 years of archaeologists using it. So the expertise that has been created this year is huge, and it is not so easy to transfer it to a model, especially if you don't know what's happening in that black box. Moreover, when we apply AI models that have been training on specific data set to another data set, a different one, we have problems. We need additional resources. These models do not perform well out of the box in which they have been created because they don't have the same characteristic. Data that have been used to create them don't have the same characteristics. So there is need for tuning and adaptation, and this process can be as much as resource intensive as starting an algorithm from scratch. Necessitate again time, necessitate expertise, because we need to make sure in any case that it is aligned with the new data that we are using it for. And finally, we have to consider also another aspect, computational and training resources for AI. It's something that is not so common to have in universities, unfortunately, and it's difficult also for small and medium enterprises. If we think about the computational power that is needed, not everybody has a supercomputer where it can train an algorithm model. It is really difficult for those that do not have access to these high-level computational facilities to really advance. Other type of challenges are more related, let's call it related to the technicalities. First of all, and the access to imagery, it has always been a problem, even before AI. It is even more now, because we know that there are so many data and we need so many data to train AI models. And the access to imagery through commercial licenses poses one of the biggest challenges for researchers and small, medium company. For this type of users, it's really difficult to obtain large volumes of images that are necessary to make a good analysis and also model training. So without having availability of good, sufficient data, researchers cannot advance because they will always struggle to develop robust AI models. So this has to be taken into consideration. We need more access to more images. Another big problem is the temporal coverage of available images that is also very limited, and many data sets provide very short time series or have very long revisited times. This means that we do not have the frequency that we need, and we don't have the data set that we need to create the efficient and good models. And this limitation is particularly can be particularly problematic for the monitoring of sites. We have seen yesterday and today a lot of examples of monitoring sites to see if they are plundered, looted, destroyed. Without the time series, we cannot do that, and we cannot train AI system to do that for us real time. Well, conversely, also, where we have, in cases where there is adequate temporal coverage, we have the problem that we don't have resolution. Spatial resolution is also extremely important. Remote sensing requires, we require good resolution data in order to be able to do detection. And this resolution, spatial resolution, is not available in many of the freely available products. So we are back again of needing commercial one. We are back again that only if you are a strong company with a lot of funding, you can purchase them. So we go back, it's a sort of a loop and a circle. The problems, one problem feed the other. So despite all these, I must say that there is a growing interest in advancing AI application for Earth observation in the field of heritage and cultural heritage. And this enthusiasm is not only limited to us as researchers or small companies working in this field, but is also includes the end user, we could call them that way, who rely on the results that we can generate using AI technologies. We conducted a survey a couple of years ago as part of the Alceo project you have seen presented this morning, a project funded by ESA. Within it, we created also a small survey and to highlight the potential of primary users of AI application in Earth observation data. The main group that we recognized as a result of this survey, the main groups that we identified as final user of artificial intelligence products where cultural heritage institutions, which are responsible for the protection and the management of the cultural heritage site or of the archaeologists that is still underground, landscape managers, urban planners, and anybody involved in infrastructure development, and archaeologists who may not be skilled in AI, may not be skilled in remote sensing, but they are keenly interested in the results of this work, of type of results that this type of work can bring. So all these groups express interest in the results generated by AI. However, it's noteworthy that it was specifically people from industries, people from landscape managers and urban planners and infrastructure developers who were the ones that were also available to support a researcher in the phase of construction, of development of AI products. And I will accelerate. So coming to the results, applications that these users are asking for are applications that have to be robust and recognizing different type of traces, applications that are very robust against prediction uncertainties. They ask for remote sensing data availability, both with good resolution and temporal frequency, and they ask also on having automated system that can alert directly on discoveries, let's call them, so that they don't have to constantly be involved in that part. So concluding and looking at our future perspective, first of all, AI system demands that we all collaborate, demand that we collaborate and bring together AI developers and expert domains in order to exchange knowledge, data, and best practices. This mix of competencies is the only thing that is going to be important in the future, because we need to integrate more the domain-specific knowledge within AI models. Archaeologists, we are very strong in wanting that ground truthing of the identifications that are done through remote sensing, and I absolutely support that. We need to put people on the ground to check if what we have achieved using AI is really there, because this is needed to train better our models. And also we need to develop robust algorithms that can be applied across various scenarios, because that's also important. So, all in all, and closing up, what we need to do in the future is really work together more. Organizations like ESA, small and medium companies, researchers, we really need to work more toward the common goal to really use EO data and AI for the good of cultural heritage. Thank you.
Thank you, Arianna, for this presentation. Is there a comment or a question very quickly? Yes, please, only one. I'm sorry.
Thank you very much for your very inspiring presentation. What you presented was you have drafted a kind of expert or expertise profile, highly interdisciplinary, which is not on the educational market at the moment. So there is no university course on that. I do not know any research group who is working on that. How do we get this expertise for our community?
$1 million question. It's
a central question. In
it is. Well, we have a problem of training from one side. Universities still struggle to prepare archaeologists and cultural heritage experts that are effectively able to move not only in remote sensing. We have already done the transition. The problem is having these people collaborating more effectively with people working in AI, which means create a common language between the two disciplines, which is something very complex. It means that archaeologists and cultural heritage practitioners have to learn a little bit of AI, and AI experts have to learn a little bit more about cultural heritage and archaeology, because so far I have seen very attempted that were not so successful, because this hybridization has not been done. And it's not just putting somebody to have a chat every now and then with the AI expert. That doesn't work. It's building the things together. And from a training point of view, this doesn't happen. This can only happen at the research centers level or departments where you can have a very strong mix of these people. Then bringing it out is another problem as well. Bringing this expertise out in the field is extremely difficult. And yeah, it's very hard. It's hard to envision ways in which we can really do that. Yeah. So now it's my pleasure to present the next speaker, Ahmed Mahmoud, who will be presenting a paper, a novel machine learning automated change detection tool for monitoring disturbances and threats to archaeological sites.
Thank you very much. Hi everyone, I'm Ahmed Mahmoud. I'm a research associate from the University of Leicester. I'm part of the Endangered Archaeology in the Middle East and North Africa project, which we mainly work in the Middle East and North Africa, trying to monitor heritage sites using remote sensing. Just to kind of give you a little bit background about the project. So the EMENA project started with 4 main objectives: to create a database for heritage sites across the MENA region, and also to track the conditions and disturbances and threats on these heritage sites. So we do use remote sensing technologies and GIS as well to support these aims. And we also develop different frameworks that uses remote sensing to for the detection for threats and disturbances in heritage sites. We do work with local partners in the MENA region, and we share the methodologies that we develop with them to kind of support them into mitigating and preserving their cultural heritage. So we have, as you can see, we have an EMENA database that is built on the open source that is called Arches. It's an open source database software. We share it with our sister project, which is called MARIA, Maritime Endangered Archaeology Project. So this database, you can have access for this database as a researcher or as a scientist, but with different level of security. So far, up to August 2024, we do have over 200,000 heritage records across the MENA region, with a lot of areas that are still empty and still need to be investigated and recorded. But having this large number of heritage records or heritage sites actually brings a specific challenge of how can we monitor these sites, right? So in order to do so, we kind of identified 4 main questions, which is, can we see a change or not in a specific proximity of a heritage site? What type of change is observed in this site, and when did this change or threat has occurred, and is it still ongoing? So the first attempt that we did was to develop an EMENA automated change detection tool, which was developed by our former colleague, EMENA former colleague, Dr. Louise Ryan, which basically uses Google Earth Engine as a cloud computing service, which is, again, it comes to the idea of the processing capabilities of large data. So that it's a simple technique, basic technique that every one of us use it, but here it's developing as a framework in Google Earth Engine, comparing 2 composite of Sentinel-2 images, and then generating the difference between those 2 images and identifying, based on a specific threshold, areas with changes, as you can see from the figures. So this technique is simple, easy to adapt, and quite rapid. But actually, it can only answer the first question, which is whether there is a change in the heritage sites or not. So that is why we moved to the second version of the EMINA machine, ACD, which is the EMINA machine learning automated change detection tool, which is the talk of today. It's a simple procedure that we normally use in remote sensing, common practice of applying supervised classification. But this EMINA machine learning ACD tool is developed in Google Earth Engine again. And it kind of analyzes Sentinel-2 level 2A data. And the idea is that you have a time series rather than just only comparing two images. In this case, you get to do the multi-temporal analysis for your case study. So there is 4 main inputs here: your study area, your heritage sites that you download from the EMINA database, and then there is the classification sample datasets, or the training sample datasets, which is, I think, our keynote speaker talked about that, which is another issue that I've been facing actually when I work in arid and semi-arid regions, and specifically in North Africa, because it creates a lot of challenges and overlap and misclassification, which you're going to see later on as well. So the idea of the tool is that it processes these satellite images, create different classification maps, and then you get to compare these classification maps to see the change, to detect the changes in your heritage sites. But in this case, you are not doing it for one single site. You are doing it for a large number of heritage sites in a specific region that you, as a user, you define. You get automatically different type of results. You get land classification map change, detection map, time series change, detection charts, and statistics about the disturbances and threats in your heritage sites. So as we do work with local partners in the MENA region, who most of the time are heritage professionals that they have limited knowledge and basic knowledge of remote sensing and GIS, and that is and also about programming skills as well. So that is why we developed this user interface. We developed bespoke user interface for our local partners, but at the same time, the user interface, the EMINA ACD user interface is also easily adaptable, and mainly the user needs to only define the dates for the time period for their study, and then they can also define a buffer zone for the proximity of their heritage site. So for example, we can say 100 meters for each heritage site. That means this would be the premises or the proximity for analysis for each site. So I'm going to quickly just show you some results for this case study. It's a study area in Libya, in northwest of Libya. It's called Beni Walid. It has a large number of heritage sites, and in this case, we are analyzing over 200 sites that we downloaded from the EMINA database. So this, just to kind of quickly show, also reflect on some of the challenges and threats to heritage sites across the MENA region, and in Libya in particular, actually, which is the threats of urban expansion, which we are seeing quite a lot actually in different areas in Libya. And this is the example when you see the KH9 Corona satellite imagery, and you compare in 1970s and compare it with a PlanetScope image from 2024, you can significantly see the urban expansion in the study area. So for the EMINA machine learning ACD results, all the results are automatically generated, so you get these land cover classification aerial time series, which will basically shows the proportional changes in the areas for each land cover class that the user has identified. So for example, we have 4 classes here: bare soil, disturbed areas, which refers to bulldozing and quarrying activities, and urban areas and vegetation. I think I will, later on I can, in the question or outside, we can have a chat about the misclassification, but you can see, you can notice that in some of the images on the chart. Another type of results that you can get automatically is the change detection between specific dates. So you get on the user interface, you get these 2 drop-down menus where it will tell you select your first image, select your second image, and then you can, from the images, Sentinel-2 images that are available between your study period, you get to choose your images that you want to do more detailed analysis in terms of detecting changes between them. So you can get a binary chain map at the bottom left here, which red areas belongs to areas with change, and black areas belongs to areas with no change. And again, there is some misclassification that is related to the overlap between bare soil and urban areas as the materials that are used for building houses in this area actually are used from the local materials, and that causes the this misclassification. You also get this chain classification map at the bottom right, which will tell you areas that used to be, for example, bare soil, and then it changed into urban, or bare soil into vegetation, and doing all that kind of cross between them. You get different type of results that are either displayed as raster images, vector data that you can use later on to do further analysis on the ground if you want, but you also get some statistical data, which is this type of 2 charts that you get. So for example, you get this statistical chart at the top, which shows the dominant sites with a specific change. So as I said, we work in an arid area, so if you have a look at that image, historical archived image, you can see that that specific site, the dominant land feature is bare class, and that is why like most of the sites are classified with the dominant pixel as bare. Bare to bare, that means that it remained as bare soil. But actually that doesn't tell us quite a lot, right? So that is why we get to do more analysis and then compare the changes in terms of pixel by pixel. So we compare between those 2 images, we see even if there is a specific pixel that changed from bare to urban, then that whole site will be selected as a site that is impacted by urbanization, for example, or as a site that is impacted by vegetation, for instance. Another type of automated change detection results that you get are the classification time series at a specific location, in this case P, which is the user will identify and say like, okay, I want to understand in more detail actually what has happened in this specific location during my study period. So for example, we have this location here. It's part of a site. Actually, the site is impacted by 2 threats. The first threat is urbanization, as you can see that. So these are buildings actually, but they are within the 100 meter of the proximity of this site here. So these sites are medieval villages that dates back to medieval farms actually and settlements. So this location here is this results actually for this location P here. But what happened is that the ACD detected this site as impacted by vegetation expansion after the June 2021, as there is a farm that actually in the neighbor new building, they built a new farm, and this new farm actually kind of the vegetation encroached into the heritage site and then caused this results to classification time series to change. And this is also validated by the NDVI time series that you can see from that chart, which is again something that we always say. This is an example of urbanization. I'm not going to talk quite a lot about it, but this is just urbanization that was detected. And this is another example of coring activities in 2 sites here. And also, again, the ACD detected the classes as vegetation. So we did some field survey validation to kind of document what is happening. On the ground, vegetation growth and construction and bulldozing were detected on the ground, but also on the ACD. But garbage dumping and looting were not detected because of the spatial resolution, the 10 meters of the Sentinel-2. And that is, again, using high resolution images might help in that. Just to kind of finally say that we do work with our local partners in the MENA region. We provide training programs in remote sensing and GIS and capacity building. We run over 20 workshops training heritage professionals on how to use our frameworks on GIS and remote sensing in general. Just final remarks, just key takeaways. I guess I'm just gonna skip some of them because I've already talked about them, but I think like one of the things that we want to further do are the integration of Landsat for longer time series rather than the short periods. And you can scan this barcode to access our EMENA GitHub repository to see the training documentation that we developed, and you can also get to see the script as well. And thank you very much.
Thank you very much. We have not much time for questions, so we are proposing to ask the question during the coffee break so that we can go to the next speaker. So keep in mind your question if you have any.
Thank you for the presentation. Then I'm inviting now Giulio Poggi with the presentation AI-driven archaeological prospection, deep learning in optical imagery analysis.
Okay, good afternoon, and thank you for the introduction. So I'm presenting the results of the project Cultural Landscape Scanner. It's a project funded by ESA in which we attempted to develop automatic detection methods to detect subsoil cultural heritage sites using AI approaches on a range of diverse remote sensing data. During the project, we had time to experiment over detection on LiDAR-based data and on optical multispectral imagery. Today, I will talk about our results on optical multispectral imagery. We know that results on LiDAR-based data are more solid so far in the state of the art. We have seen yesterday the presentation about the use of AI to detect Maya structures in Yucatan, and so we can measure this solidity by analyzing the results and the model and also the diffusion of the applications in the literature. We have problems in using AI on multispectral imagery, especially for subsoil features, so features that are not has not a prominent topographic expression, let's say. We define some issues that are the same issues that we have when we visually look at multispectral data for archaeological prospection. Those are that subsoil features have alternating seasonal visibility, so their visibility depends on the condition of the soil and of the vegetation that covers them. And also the visibility is a little bit subtle compared to the topographic visibility of some features. Also because we are working mostly in open areas that are affected by agricultural activities, in urban expansion and infrastructure development, compared to LiDAR that is often applied to forested areas in which the preservation of the natural terrain is a little bit better. We have the problem with low-level standardization, so we struggle to train classifiers on features that are not similar to each other. There is a high impact of landscape characteristics. Looking at the image, the archaeological features are not the most evident things that we can see. They are a little bit subtle compared to modern characteristics, and also we have limited dataset availability. That is probably a common problem for this kind of applications. What are some viable solutions that taken from literature? We can, for example, summarize information contained in a time series of images and compute statistics and indexes over large periods. This is a technique used especially in the last years through the development of collaborative platforms as Google Earth Engine, which allows to handle large time series. And this type of approach is usually good to highlight trends in the data, but has the limitation of probably don't see spot information that may appear in over these time series. That is the case of the visibility of archaeological features. Or we can use, for example, dimensionality reduction method, try to summarize in a limited number of products information contained in large data sets. So we can also screen the multiple images, finding the images in which we have the best visibility for the features we are interested in, and then analyzing just those images, which is kind of a standard approach. The fact is, the more image I analyze, the more chances I have to get the visibility of the features. And then, of course, my interpretation of those features would be better. So our idea was, how can I theoretically analyze all the images without spending so much time? That's why AI can come and assist this kind of procedure. So we created a data set for building a machine learning framework with data and baseline models. So we wanted to find solutions that address alternating visibility of the subsoil features on temporal series with machine learning. We wanted also to have the possibility to test various architectural configuration of deep learning models. And also we wanted that users can experiment with preprocessing pipeline. So we saw yesterday that on LiDAR we can apply visualizations that enhance the properties of topographic characteristics. What are the best preprocessing steps for multispectral images for AI detection? We wanted that this dataset is open, so we want that users can build advancement on top of baseline models. So for these reasons, we developed this map dataset. This is a multi-temporal, multispectral dataset for paleochannel segmentations. We started with sort of easy features to detect, paleochannels, which has a lot of common characteristics with archaeological structures, but maybe it's more easy, so we started with, and we wanted to see what were the performance during this task. Also because we wanted that this dataset to be free, so we had to use freely available data. So we used Sentinel-2 images, which has a resolution of 10 meters, so we could not go to detect small traces. We selected 1 year of Sentinel-2 images, selecting one cloud-free image per month in order to cover the area in northern Italy of 1,600 square kilometers. And we wanted to build this baseline model for semantic segmentation, so we developed a PyTorch implementation. The problem in creating the dataset is how do I label a multi-temporal dataset? Because if I look at the same area over multiple images, I see that the visibility changes. So which label is correct for each image? Our interpretation is that we had to label each image individually because the visibility is changing. So we are providing to the model the correct label for each season. And to select the best season to start annotating, because we don't want to annotate 12 images, we wanted to reduce as much as possible the annotation, and then in testing, in the inference phase, predict on multiple images. So we want to do a little work for labeling in order to make the model to inference on a lot of images. So we reduce the labeling to 3 periods selected by empirically analyzing the visibility of the features. So the best periods, and then we selected the third one in between in order to have 2 months separate each period. We split the data set with geographical split to account for spatial autocorrelation, and we draw on the third column, you can see the number of instances, the number of labels that we draw for each data set. Each label accounts for 2 consecutive months. And then in test, we labeled 5 different images, including images that were not used in the training. So, for example, we included also May and October, which were months that were not used to train the model to test generalization over different temporal periods. We created the training set using RGB. So our preprocessing was just basic. We extracted just 3 bands from the Sentinel-2 cube, so the Sentinel-2 multispectral band. And we created 2 training sets, one with 1 image per associated with a tile dataset, and the other training putting 2 images for the same label. And on top of this, we built 3 deep learning architecture to see if there were differences between architectures, to see which model was performing better than the others. And those are the results. As you can see, we achieved better performance using the second training set, so using the double of images than the first training set, although we didn't get as much improvement as we expected. Probably because the images that we trained with the same label were very similar, so there were no much information for the model in those training. And we got the best results in November. The IOU that we've seen, it's 0.29, so it's a little bit way lower than what we got, what were shown yesterday on LiDAR data, where IOU was 66 or something like that. And the model, we got similar performance to months not using the training, so we can assume that the model generalized quite well even on months that are not used in training. So we can apply it on all the images for the whole year. How do the masks look like? Those are the results for the prediction masks for the 3 architectures. And we got slightly better results for UPerNet and the UNet, also because we got a higher recall. That means that our masks cover completely or cover most of the ground truth masks, even if the masks are not precise. That means that the masks are a little bit larger than the ground truth. So we have lower precision but higher recall because we are actually detecting the paleochannels. YOLO V8, however, is more precise. The lines are more resemble more closely the labels that we were using in the training. what is the, say, the expected outcome is that if we take all the information that we got by analyzing a lot of images over the temporal series, and we put all the information together, we can reconstruct, we can reference each observation as part of a more complete pattern, reconstructing the continuity of the traces, and then facilitate the interpretation of the traces. If we take just the true positive pixel detected by the model, we can see how putting more images on this sequence, we can actually have a better look at what the network of paleochannels looked like. So these are the results. I want to thank all the people that work together for this paper, which is in preprint on TechArchive. And then we have, of course, open challenges that users can work on top of this data set. For example, exploring multitemporality. We didn't cross-reference tiles in the data set. And we wanted to experiment about preprocessing. We just took RGB images, but what if I took other bands or calculating indexes or whatever? And we wanted also to define good metrics for archaeology, because we have seen that the IOU gives a roughly representation of of products that in practical are not so bad as they look like on numbers, on just numbers. Thank you very much.
Yes, the question will be taking them at the coffee break. So I would like to invite now Tamer Otzop with the presentation titled Monitoring of Cultural Heritage Assets in 3D plus Virtual Space, an approach by using ADL4CH.
Thank you. Thank you. Good afternoon. I'm really happy to be part of this unique event, and I thank you to organizers for this unforgettable time. And firstly, I want to say the title, The Monitoring of Cultural Heritage Assets in 3D plus Virtual Space. This is an approach. Our project is ongoing. And the approach is more than the 3D modeling we are dealing with, and real-time data and environmental conditions we are integrating this approach. And this approach will allow us to explore the heritage sites and remotely, but continues the monitoring potential risks and offer an interactive experience, especially for enhancing the public engagement. We put the vision and strategy of this approach. The vision is to make this cultural heritage is accessible for several. Everybody must access the data and the results, and it would be visible and affordable and easy manage. This is the important for the approach. Then we make simplifying the complex systems, this actionable insights. We aim to establish a sustainable, technologically advanced, and preserving these assets. We use both satellites and UAV. You know, the Earth observation is the process of gathering the information from the Earth, from land, atmosphere, and the marine by using different platforms. Today and yesterday we talked about mostly the satellite-based Earth observation. Now, we using the UAV data mostly, then satellite data will be the complementary for our approach. And we want to create a heritage for all, and we want to turn the complexity of the system to the actionable simplicity. Our strategies is divided into 3 pillars. One is innovation and leveraging the AI and deep learning and in 3D virtual space. real-time accurate monitoring and visualization and cultural assets. These assets are tangible assets, not the intangible in the language. And collaboration is important for the building a global partnerships for these efforts. And the sustainability is the more important and the cruise, and implementing this cost-effective monitoring system is critical for the approach. This line shows the value chain of the system, starting from data collection, processing, and visualization and results. And this is the simplified system, how it works. As you look, the low-altitude drones, when we are using mostly, we are targeting the structures and taking the transecting the images by this camera, high-resolution camera, and the main control point will evaluate and confirm the damages. If there are any not, we use the modeling, DL modelings, and damage is confirmed and not confirmed, and we'll go to the visualized platform. This platform will show the data results and the insights, and you can access and use the system. And the objectives is mainly to detect and identify the damages and different changes in the cultural heritage assets. The key features, we use the Copernicus system also for the baselines and the digital elevation modelings and physical assets. We are dealing with the mostly monuments and the geospatial data. We include all of them in the cloud system and the main control point and virtual globe. We will monitor the digital twins of these assets in 3D virtual globe, and the monitoring platform utilizes the AI-driven, cost-effective UAV systems we would like to use. Everybody can buy from somewhere the UAV and will put this high-resolution camera and will achieve their results using the deep learning models. And what's the significance of the cultural heritage? Everybody knows, but I would like to remind once more. This is the connection to our past, and this is unique for us and inspired our future. And cultural heritage is increasingly recognized as a vital, changing in this complex world, and leading to emergence of new practice and new concepts, and also the valuable commodity for in our life. The importance of this cultural heritage from generation to generation, it's our identity, continuity, and the values of the communities. Every community has their identity using this cultural heritage. And also if you look to this feature and educational value, promotion, social cohesion, economic benefits we can get, and the cultural diversity, inspiration, and legal, ethical importance and environmental significance are the others significant parts of the cultural heritage. Okay, the next one. What are the trees? And trees, as everybody knows, today's word, and rapid urbanization, man-made approach is we are including, and the aridity, pollution, the humidity, high solar radiation, and extreme heat waves, and the winds, wildfires, and hazards and earthquakes. These are the main threats. Every day we are facing with these threats, and this is the potential for the substantial harm inflict the cultural heritage assets. This picture shows from Turkey, for example, the last one was the 2020, the wildfire. It was very close to our homes and the cultural heritage area. It just 1 hour ago is stopped by the actions, and we lived this kind of trees very frequently in the system. Okay. Now the challenges related with the digitization, for example. If you look the cultural heritage in the world, just 15% digitized format. Great majority of these assets prone to corrosion and degradation due to the age and the other reasons. In this time, the traditional methods, if we look the inadequate, the complexity of the large spatial scales of these structures, making detail analysis and decision-making difficult. And if you look the right side, the research deficiencies, lack of young engagement, lack of public visibility, digital skill gap, and systematic knowledge gap, these are some of the important challenges in the working the system inventory methods, and difficult to get the good results from the complex data. And inventory methods also, we are applying conventional systems and are not efficient for the protection of the cultural heritage. What's the solution? With what I said, our vision and our strategy, then we are proposing a new solution, and this is a low-cost system and speed up and auditing process for the cultural heritage assets. And this is a new prototype, AO Powder unique camera, high-resolution camera, will be mounted to the low-cost system, low-altitude drones, and will automatically detect the damages and changes, and with using the DL models, and we will geotag these changes and the models enable us to monitoring them in a digital twin in 3D plus virtual world. This is the location where I live, is the south of Turkey. It's located here. We call this the Muğla Park, and we also defined the heritage concept. This is another thing, because there are the different layers of the cultural heritage, multi-mixed heritage we facing a holistic system. And this holistic system, you can find in the same present time the agriculture, historical, and natural ancient cities together, all of them. All of them are integrated because they live in the same lifestyles they use, for example, in the agricultural olive production areas. And now today we are using the same woods of the olives, for example, and those are the different type of the value assets and the different layers and the time rules, and we can use also the tourism rules also for this holistic approach in this area. Muğla is the region, is remarkably rich, and the universal heritage characterized a unique cultural heritage, archaeological, geological, historical attribute from the Karya time, 2000 BC, to today in Karya, Byzance, Roman, Ottoman, all the layers you can find in the same area. You can walk in one day, is different layers, and you can see this kind of assets in one day by walking. And test site is, as I said, showed the threat, the wild fire happened, and we protected zone is about 415 registered cultural assets we have in the city. These are the examples, and from the buildings about 200 years ago they constructed. Archaeological protected sites, also the same area, and the natural protected sites we have, and both those are the what we are thinking to preserve the system. Okay. The value chain of the project shown as like that. This is the proof of concept. Some parts are developed, some parts are prototype, still some parts in the just research stages. And CultureMind, we did all the data gathered in the system, needs and requirements finalized, collection and processing and reconstruction still continue. And we are on the technology design and development part, and later we'll test, demonstrate, and implement the system. We will create the comprehensive framework at the end of the approach, and will show the easily, simply, and manageable system. And this is the first phase. What we are doing, we are gathering the data and integrating, and later 3D constructions using the surveying the flight site, and this flight site taking the preparations and photogrammic data. Is it time? 1 minute. Oh, it's 1 minute. Okay, I must sleep. Okay, then I will continue very fast. And these are the another part, digital twin flowcharts, going to how to do it. And we use all the systems, geographical information data, and both. And let's go. How to collect the system, the features, and we use our apps to take the inventory data. And what's the inventory system? We already did this platform. We can enter and query, analyze, and report. This is a culture book as a kind of pages, and different pages shows the archaeology, for example, rural architecture and urban architecture, and the other sectors. This culture book is already done, and the different layers we can easily analyze using this digital inventory system. And these are some examples showing the archaeology. Then how can we see the data? This is the ICOMOS and the Turkish inventory system and data types. And just 2 minutes buffer. Okay, I'm sorry. Okay, let's go. Another one, the archaeology sites. Again, these are the important, because you must link all the data, what you are doing. You are looking from the space back, okay, but what are you doing and what are you looking for from the ground? And how to collect the data. These are the showing. We designed the camera, as I said. This is the air-powered camera, high resolution. And price will be 300 and 500 euro. And the system definition is like that, the artificial intelligent camera module, and transmitting all the location information to the system. And 4-unit image, artificial intelligence, and GPS, and the GCM unit. And the deep learning model, we use the Yola-type based algorithm for this teaching and training the system. And the features of the modeling is showing is like that, detection, some of the accuracy levels, and how to collect, utilize, and the expert involvement is critical. And at the end, all the system will be in the web-based GIS platform. We will track everything from there in this platform, map tools, analyzing tools, and the photos, movies, everything inside, and the 3D virtual globe, and the digital twins. And the key features passing through that one, and the software architecture, how it will be, and the real-time monitoring. And again, the data management and technical things. And at the end, products and service, we have our target, tourism, real estate, finance, and valuation, and some competitive advantages we are showing. at the end, the team is important, of course. We have a capacity, very well experienced people and stakeholders. All the municipality, ministry, and the public people are the platform. They are supporting our project. This is the critical for the projects. You must go together, not the technician, not the scientists, and all the system must go together, that they must understand what you are doing easily. And we are a 4, and at the end, this is my value. I started from here, is next door to Esrin. This is the 95. Then I did coordinate the Turkish first Earth observation satellite. Now I am here like that. Thank you for attention. Sorry about
Thank you, Tamer. No worries. Okay, so we move to the last presentation before the coffee break. Thomas Makivicius, please, from Low Earth Orbit to Cultural Heritage and Horizon Europe MOXIE project. Tailored cold plasma generated atomic oxygen for non-contact cleaning sensitive works of art. I finished the time.
Okay, I will try to do brief. Thank you. Well, good morning, everyone. Thank you for the opportunity to share today this exciting new research on atomic oxygen, which is naturally found in low Earth orbit, and it's actually, well, very harmful for satellites, as it's a. But when used on the ground, it can actually be very helpful for cultural heritage conservation as a method to clean sensitive works of art in a non-contact way that is not possible with traditional methods. And two NASA scientists, Bruce Banks and Cheryl Miller, presented a groundbreaking concept to apply AO, atomic oxygen, for non-contact cleaning of a lipstick vandalism on an Andy Warhol painting and fire-damaged workshops now 26 years ago. This, at that time, a bit science fiction treatment made headlines in the 1990s, but AO remained in limbo for decades. Today, in a different time and context, AO offers a non-contact way to remove challenging carbon-based contaminants without health and environmental concerns. And I'm pleased today to share this results in progress of European MOXIE project. And well, I will briefly speak of the MOXIE project, carbon-based contaminants, which we're targeting the origins of AO from NASA to art conservation, and how we're tailoring AO for cultural heritage conservation. Well, this is a 4-year project which was launched in November 22, and we are now in the midterm. It's coordinated by Ghent University, and it includes 10 organizations, and the picture shows our team, which has grown since. In 2023, MOXIE began also working towards coordinating a formal group of 3 Horizon Europe projects, which work on green technologies, and which includes altogether 53 research organizations. And these are our main work package leaders here on the slide. Well, carbon-based contaminants constitute a significant portion of soiling materials listed here at the top of the slide. The composition of environmental pollutants contain a large share of carbon-based matter, which could be treated using AO. Soot is among the most pernicious carbon contaminants. At 1080 nanometer, soot is much smaller than typical porosities in art materials. And here in the SEM image, the white debris is soot on acrylic paint, and the scheme gives a comparison of the soot size compared to human hair and other materials. On the west coast of the United States, but also in Italy and Greece, we're always aware of the increased impact of wildfires on environmental conditions we live in and the objects we conserve. Well, sustainable preservation of cultural heritage is inherently linked to United Nations 2023 Agenda on Sustainable Development Goals. Yet, conservation field currently really lacks empowering green technologies, especially in cleaning treatments. And contact cleaning is particularly problematic with sensitive, porous, and fragile materials where the available methods risk abrading the surface and transporting contaminants even deeper in the substrate. AO may offer an alternative non-contact approach to remove carbon-based contaminants. AO is a space environment material found at altitudes 80 and 1,000 kilometers, and it's a single oxygen atom species produced through influence of solar radiation on molecular oxygen. AO is highly unstable and reactive and is a major erosion factor to spacecraft materials, as you can see here on the damage on Eureka satellite. Among the main oxidizing species, AO oxidation potentials is 2.24 electrovolts, is almost double that of O2 oxygen molecule. The challenge of MOXIE project is bringing this out of the swelled material to the conservation practice, since AO is extremely short-lived on the ground, just few milliseconds. During past 40 years, NASA and ESA have investigated AO interactions with spacecraft materials and developed simulation systems conducted in low-pressure vacuum chambers, here on the slide, which cannot be yet realistically applied in conservation. In an alternative approach, Bruce Banks and Sharon Miller devised a device to produce AO at atmospheric pressure by flowing molecular oxygen through a high-voltage, low-current DC arc. The technique was used to a fairly well-known case dating late 1990s to remove lipstick from early Andy Warhol painting titled Bathtub, here on the slide. In our MOXIE approach, which is being designed to tailor AO for specific materials and treatments, we have been developing a system that generates AO using pulsed radio frequency power in cold plasma instead of DC arc. The system includes an AO generator, gas flow controls, a function generator, a broadband radio frequency amplifier, real-time plasma parameter probe, and a magic network, all settings that allowed us to tailor AO production. In this slide shows the logical scheme of our AO generation and cross-section of the nozzle with two gas flows, one to generate AO and one to shield the beam from external environment. Well, so what exactly does the device generate? As you can see here in the image 1A, oxygen atoms can transition across different states depending on energy levels. We aim to produce the ground state oxygen, well here called 3P, and the excited state 1D, where P and D refer to the orbital angular momentum, and 3 and 1 indicate the multiplicity of states. To simplify, 3P is the lowest atom energy level possible, while called the ground state, while the 1D is the energized state marked as 1B. The excited oxygen can react with carbon even better, but it quickly transitions to the ground state, so only the ground state arrives to the surface, as you can see here in equation marked 2. To generate AO, we use helium with around 0.3% of O2, which we split by electron impact dissociation using radio frequency plasma at 13.56 megahertz. This slide illustrates the AO generation and cleaning process of blast substrate. It's necessary clarification that MOXIE device does not use plasma for cleaning, but plasma is used only to break down oxygen molecules into atoms. And here you can see equations that show that reacting with carbon materials, the products are volatile species. And here to investigate the beam that delivers to the surface, we used optical emission spectroscopy to examine axial and radial density of excited oxygen within the effluent. So it basically shows that the excited oxygen does not survive more than 0.5 millimeters. And basically the cleaning action is done so it doesn't arrive to the surface, and the cleaning is done by the ground state oxygen. So tailoring the surface temperature is one of the main challenges. While testing the treatment distance between the nozzle tip and the surface, we identified like sweet spot ranging 3-6 millimeters, where it is still enough AO, but the temperature is lower enough. Naturally, it will depend also on continuous exposure time, as illustrated in image 2. So one of the approaches is just like a fast movement of the nozzle across the surface, doesn't allow it to accumulate for the temperature. Well, we apply also other strategies looking how to reduce the temperature, for example, like using modulated second wave radio frequency harmonics and pre-cooling helium gas and other ways. And here is our testing of using time-dependent FTR on soot and other substrates, identifying conditions at which oxidation is faster and which other products are produced, for example, ozone, which does not depend on, in this case, on applied power, but only on the concentration of oxygen in the mixture. To facilitate its application in conservation, we're also developing a simplified atomic oxygen sensor for conservators, where they could, which is based on quartz crystal microscale, which can sense mass loss in microgram scale. And while we test AO on different cultural heritage materials, it focuses on organic substrates, sensitive paints, pigments, porous inorganic materials that are typically difficult to clean with traditional materials. And our challenges are to develop contactless cleaning without health and environmental concerns, which can be tailored for different cultural heritage surfaces. So far, we have been successful identifying several contaminants where atomic oxygen works, such as soot, surface dirt, wax on metals. We also addressed like cotton, like fingerprints, lipstick, markers, graphite pencil, even coffee. And we went further to test microorganisms, biocides, which is another big problem in cultural heritage, and other effects. And one of our early tests was actually repeating NASA's experiment with lipstick. We received from them a sample that was used on Andy Warhol, which was analyzed, and we carried out, we couldn't resist the temptation to repeat the same sample. So here is NASA's example, and here you can see our result, removing half of the lipstick. So it's being also tested, like here on the left, you see on a natural dirt from it's a paper from 1896, which atomic oxygen can remove, and also some model mixtures that are used in conservation typically to imitate cleaning. We focus our research on soot and fire damages, which is a big problem in conservation. And for this, we devised our system how to apply in a repeated way soot aerosols. So this is like a drum with a rotating carousel, which actually was first tried at NASA, and we repeated their design. And here are some results, like cleaning soot from plaster, which is typically difficult to clean because of its softness, porosity, and sensitivity to moisture. So you can see like pristine soot, and then cleaned with atomic oxygen, the result. And here is the same plaster, pristine, and cleaned from soot using atomic oxygen. So here is an image of SEM showing pristine, in the middle soot, and then cleaned with atomic oxygen, really showing on microscale cleaning. We also tested the effects of atomic oxygen using changes in roughness, like on micro roughness, and basically the micro roughness increased roughly by 0.1, 0.3 micrometer, which is below the perception capacity of human eye. And yet another sensitive substrate is gouache on paper. Here it was suited with soot aerosol, which was treated with AO, and here you see the result on the right. And in SEM, you can see the microstructure of the gouache surface was completely obfuscated by soot and then recovered using AO. While FTR analysis did not show particular chemical changes due to atomic oxygen cleaning on paper substrate. And then, we tested soot was removed from cotton duck canvas samples after the treatment. The surface appeared to the naked eye to be in a very good condition, and even lignin impurities were not affected and preserved. So, although in SEM it was still possible to notice small scuff marks in the fibers. And here is the cotton duck with gold and acrylic paint, soiled and soot after AO cleaning. And the same before and after images under the Hyrox microscope. So we also tested other materials such as AO effects on some fatty acid exudates, which is a problem on modern materials, plastics, modern paints, and they can seriously affect works of art. The exudates here were identified for analysis as stearic acid, which were easily treated using AO at fairly low temperature, around 40 degrees centigrade. Here is another example of AO cleaning of feathers soiled with AO, and then image of SEM before and after cleaning. Last week we tested soot cleaning on a test painting in collaboration with Courtauld Institute of Art, London, and Professor Aviva Bernstock team. So in summary, the exciting novel application of atomic oxygen and other reactive oxygen species, such as plasma-activated gels, present many challenging multidisciplinary scientific questions. What we want to know so far is if AO cleaning is possible and provides contactless treatment opportunities. The AO process can be tailored and upscaled. The method is safe for health, and the environmental production is, includes benign byproducts. And liquids and solvents are not required. The method is volatile and non-thermal. As a natural element, AO may be culturally accepted by indigenous communities. AO may produce new ways to completely remove biological contaminants and biocides, and it can be combined with other conventional treatment methods. So we're looking into upscaling AO and transferring it from research lab to museums, and this is one of our early prototypes, which soon will be leaving to University of Pisa for further test and analysis using mass spectrometry. And looking at the future, depending on the treatment needs, both small size and cleaning spot and large area can be useful. Our prototype works well on small areas, and larger areas can be treated using XYZ stage or robotic arm. We cannot really increase the spot size as it will get, well, very hot. But we can replace the spot with a line, and add another line, and then another line, and make it into a scanner-type device that could move across the surface using motorized stage. And we made a little experiment, which actually seems like a plausible concept for the future, which we want to develop in our forthcoming project called FireSafe that we're currently developing. So, and I would like to thank you, my co-authors, and you for listening for the presentation and for opportunity to be here. Thank you very much.
Thank you very much. So just to explain better, if you have any specific question, we ask you to ask them directly during the coffee break to the different authors that we had during the afternoon. So now we have the coffee break. It will be shorter than the others. You only have 15 minutes because we want to reconvene here by 4:15 in order to be in time. Thank you.
Okay, sorry, we need to start with the conference now. Perfectly fine. Then check the last picture. You need to check it because I think it's a good one. Okay, so we start with the last session. Thank you for being so patient and resisting today. So I'm going to present the first presentation, which will be given by Ciro Manzo. It is about ESA, third party, and Copernicus contributing missions.
Thank you, Yolanda, and thank you for inviting us to present the commercial AO data and service for cultural heritage. I am Copernicus Contributing Mission Coordinator, and today I'm presenting also on behalf of Peggy Fisher, who is the AO third-party mission and Copernicus Contributing Mission Manager. Okay. As you can see, ESA is buying commercial data for two main programs. The EarthNet third-party mission, that is focusing more on data for R&D and science application, and for Copernicus Contributing Mission, that is focusing more on operational needs of public application. For what concerns EarthNet third-party mission program, it consists basically of 50 satellite missions from commercial and public organizations and promote the free availability of this data for research application. As you can see, there are different application area, different domains in which the TPM data are available: SAR, optical, atmospheric mission, and radio frequency. And in the context of cultural heritage, the remote sensing, as you have seen in these 2 days, is demonstrating its capability in supporting the cultural heritage domain. In particular, because it is able to identify and monitor and analyze area of interest and is able to cover different application area domain. In the TPM, we have more or less 30 projects that are focused on cultural heritage applications. The main domains in which we have the usage of the data for cultural heritage are historical site stability and integrity, the impact of climate change and cultural heritage, risk assessment, archaeology, and urban sprawl monitoring. Here you can see an example of nighttime thermal data collected with SAT-VU over Rome, where you can see that the usage of high-resolution thermal data is able to analyze the heat waves that happen in a city and how the difference of tree coverage can imply the reduction of heat waves. Indeed, you can see in St. Peter's Square, where there are basically no tree, you have a lot of heat retention, while here in the Castel Sant'Angelo, the presence of a tree enables obviously a net reduction of thermal emission. Here you have another example with SAT-VU, because the thermal data can be used for monitoring also the fires, and in the context of cultural heritage, the monitoring of fire risk is a key in some area, in particular in the south of Europe. And one point that we want to highlight for what concerns the SAT-VU data is that probably in the near future, the TPM user will be able to access the HotSat-1 6-month archive. So there will be an announcement of opportunity on TPM website. As I've shown you before, we have bunches of different sensor domains, and here you can see also the opportunity for taking some sample product for 13 from these 13 different data providers, in which basically you can see you can give a look to the data. You can download this sample data. Here you have also the link to get all this information. How to access the TPM data? Basically, you need to prepare a project proposal, submit it, wait more or less 6 weeks, and then you will be able to collect the TPM data. So this is a great opportunity for research and development applications. Where you can find all the information regarding TPM, simply you go here on earth.esa.int EO Gateway, and if you go on TPM terms and conditions, you can get all the information that you need. Special attention on ESA is also paid on the outreach activities, where basically here you can see on this link all the success story on the usage of TPM data. And among these, you can also find some success story on the usage of cultural heritage applications. Now let's move to the other part of the presentation regarding the CCM activity. ESA is the entrusted entity of European Commission for procuring data for Copernicus program. Basically, the Copernicus contributing mission are complementing the Sentinel family, so the current set of Sentinel, and is also preparing the uptake for the Sentinel next generation, and is focusing mostly on very high resolution of optical and SAR missions. And recently we are also starting to add new commercial domains, such as hyperspectral, thermal, and atmospheric composition. As I mentioned before, ESA is procuring this data with a new setup that is called the Dynamic Purchasing System that started in October 2022. More in a practical term, ESA is providing data, is serving the different Copernicus services for their needs in terms of collection of data for Sentinel complementation. And the industrial policy that we follow is basically to give preference to EU data for data buy, the gradual inclusion of data from European space startup, and give a lot of importance to the data quality, because the Copernicus services rely on the quality of this data in order to perform their processing chain. This is an overview where you can have all the established data providers, European and non-European, and then here you have the emerging CCM, so all the ones that we call it as emerging data providers that are, okay, you can see here, basically are 9 different companies that are covering different domains. Cuva Space is covering hyperspectral, Satlantis and Absolute Sensing are covering the atmospheric composition, Constellar, Aurora Tech and DiceTech are covering the thermal infrared, Aerospace Lab and Eurosat and Prometheus are covering the multispectral domain. What's new with them? Basically, we are defining what will be the long-term evolution of Earth observation. We are supporting basically these data providers and their constellation, which will enhance the capability of the Earth observation to collect data in a faster way with a higher reactivity and with a new concept in terms of processing. For instance, we have some data providers that offer onboard processing for production chain. We have some analysis done for AI onboard processing that will enhance also the capability of the constellation to provide also added value product. These 9 missions have been contracted up to 5 years, so we are also ensuring them a long-term contractualization in order to establish their service, and we aim to support the Copernicus services and also the evolution of the Copernicus services, because hyperspectral, thermal, and atmospheric composition are quite new in terms of Copernicus contributed mission data provisioning. Let's move to the established data providers. This is an example coming from the large data sets that we have as CCM, because the CCM supports the provisioning of large coverages of Europe. Basically, you have a full Europe coverage each 3 years since 2012. This means that you can have an image in some area of Europe, you can get the data, one data in 2012, 2015, 2018, 2021, and 2024. We are completing it in a few months. Basically, you can get the data from 1 to 4 meters. Obviously, each data set has its own specificity, but this is the range of resolution that you can get. You can access here the information to access to this different satellite systematic collection. Going more in detail on this application, first of all, because it's a nice example of archaeological site in an urban area. So the Macellum site in Pozzuoli has been visible in these 2 data sets in 2014 and 2021. And in this zoom, you can see that in 2014, you can have this black area. Basically, it is the water that often is present in this archaeological site, while here you see a bright image because basically there is no water. Obviously, the frequency of the presence of the water in this archaeological site is much higher than these 2 images. But just to show you that if you merge the high resolution of images with the higher frequency, you will be able to monitor the archaeological site in a new unprecedented way. I'm changing the... This is another interesting example that has been coming from emergency activation of a fire near ancient Olympia, happened in 2021. Basically, we collected for emergency pre-event and post-event images with the WorldView 2.3 and Pleiad 1A and 1B. The comparison of these 2 images, of these different images, was enable emergency service to define this grading overview map, where you can see in dark red the area that have been destroyed or heavily damaged by the fire. Another interesting application regarding Copernicus contributing mission is regarding the multi-risk, because the risk and recovery component of emergency in 2022 have been activated by Greece government in order to define a multi-risk analysis over Delphi and ancient Olympia. As you know, these 2 areas are exposed to different multi-risk. So we can have, during the period of year, we can have different kind of risk that can affect this site. The fire during the summer, the flood during the winter, soil erosion, landslide, earthquake. So the support of CCM in this context was to provide part of the source of information that are necessary for doing this kind of job, that enable them to define a set of products such as the exposure, hazard, vulnerability, and also to define which are the period of year in which the public access is more or less risky based on this multi-risk analysis. This is the last example. Yeah, this is the last example that we have regarding the man-made destruction of cultural heritage. This is a critical element, also considering the current situation worldwide. This is an example from Middle East, where an image acquired in 2014 shows the presence of the temple, while in 2021 you can see the same temple that has been destroyed. You can have different examples worldwide. For instance, the Buddha or Bemani in Afghanistan. So the cultural heritage is exposed to the war condition, and there is a Copernicus Security CESA on external action that are working on it, and today there was also a presentation from one of them. Who can access this data? That I guess is the most interesting point of this single part. Basically, the data that I showed you, in most of the cases, are accessible to Copernicus services, institutions, research projects funded by European Union, public authorities, while Copernicus services and research projects funded by European Union can also task satellite. I put here some link where you can get the full set of data access portfolio, so all the different data sets that are accessible, and also the collections that you can access. Last slide is just to recall that at the beginning of December we will have the VH Roda, that will be a conference where we will discuss about very high resolution data quality, and everyone is invited to join this meeting. Thank you for your attention.
We don't have time for questions because we are delayed. So our next speaker is about the Cosmos SkyMed system and is by Flamini.
Yes. Okay. First of all, thank you to all the ISA staff for the invite, and we are glad to be a contributing mission. So we are going to present, we have seen a lot of application. Now we are going to see data where we can build up this type of application. As said by the speaker, Ciro, from ISA, we are ISA contributing mission by the beginning of the program. So I'm Alessandro Flamini. I'm the sales responsible for the European market and cover ISA as customer. Cosmos SkyMed. Cosmos SkyMed is a constellation, is owned by the Italian Space Agency and the Ministry of Defense of Italy, and is manufactured by Thales, Telespazio, and Ageos, that is the company which I belong. The worldwide commercialization, and so also the relationship with ESA and all the Copernicus activities was managed by Ageos. The history, very few numbers. At the beginning, starting from 2007 up to 2010, was launched 4 satellites. In 2022, 2 satellites of the new generation was launched, and now there is planned the building and also the operational activities for additional 2 satellites. That means continuity, that means data for all the application and for all the services, and also monitoring. That is for sure relevant for the cultural heritage application. Cosmo and Cosmo second generation have, in a few words, have ascending acquisition and descending acquisition. That means that we can revisit a specific area after 12 hours, and with the interferometric capability in 16 days. We will see later on what we can do with the interferometric capabilities, but in very few words, we can monitoring the vertical movement of all the man-made infrastructure and ground. So that is relevant for cultural heritage application. The sensor mode, the image mode of the satellite of the entire constellation was a ScanSAR, 30 meter of resolution for a SWOT very huge, strip map and spotlight. Spotlight is the metric, submetric images, and we will see that with strip map and spotlight we can do several applications. Cosmos SkyMed second generation, for sure, being the last satellite launched in the 2 years, so starting from 2022, have a better resolution, less noise, so it's very good in terms of quality of image. We are speaking about big satellite, not small satellite, so we have sensor and stability of the constellation very proven, and that can be the basis of a huge stack of data to do a lot of activities. We can build, for sure, there is the dual pole and quad pole, also RGB image. I don't know if all of you know the SAR satellite, but is an active sensor, so it means differently by the optic one that make a picture, send the signal and take the measure of the time that they spend to come back to the satellite, and is black and white. So we will have an image that is at gray color, but thanks to several products, and we will see later on, but also the dual and quad pole, we can build RGB image, so similar to the optical one, to build again application. Interferometric capabilities means that we can see the same area with the revisit that I mentioned before, 16 days, at the same geometry, with the same stable sensor that was hosted in different satellites, but that allow us to have this data set to make analysis, very precise analysis, and we are speaking about millimeter measurement from satellite of the ground stability of the installation. Cosmo have a long history, as I said before, and we have an archive, and as an agreement with the Italian Space Agency, that is the owner of the system, and as political, commercial policy, EGEOS have built an archive over big cities, 200,000 inhabitants, but also UNESCO sites. So all these sites are covered by the beginning of this constellation. We can start and we can see several products in order to allow you to think about possible and future application. Multitemporal coherence. Multitemporal coherence is an image, is a color image that identify what is stable and what change in 2 different dates. So we will put on the red channel the date number 1, in the green channel date number 2, in blue channel is the coherence between the 2 images, so is derived by an algorithm, and we will see, we can see a screen over airport of Fiumicino, that what is white is stable, what is red, we will have an input on the changes on a specific area. What is green is changed starting from image date number 1 up to date number 2, so it's present in date 1, not in date 2, and green is the same, is present in the date 2 of the image, while in red is not present in date 1. What we can do with the interferometric analysis? We can measure, thanks to the backscattering properties of what we are going to observe, the position, geographical position, so X and Y, but also the Z. So the movement that will be in a specific area for a specific target, and also measure the velocity and the evolution in the time. So you can see this is an image over an industrial site, but we will see also in archaeological site, and there is the movement that we are going to detect. The red one is the movement, the highest movement, the green one is what is stable at the end. And we can move also in the time, so in the period, not only the movement for a specific observation in one image, but consider that we have a stack of images, we can measure the evolution of this movement. And after, for sure, we need a support by expert to understand what is the causes of the movement. For this cultural heritage topic, for sure, we can monitoring building stability, ground subsidence, landslide, earthquake, and volcanic phenomena that can have an impact on archaeological site, historical building, bridge, monuments, and landscape, because natural can be also have a value. We can do with Cosmo, but for sure also Europe are building this by Sentinel. So we will be presented also later on, but through the environmental agency in Denmark, so in Copenhagen, there is a service paid by the European Commission that using Sentinel-1 are measuring this movement by the Sentinel images. You can understand, starting from the image that we have seen before, this is Castel Sant'Angelo, that the density of the image by Sentinel-1 have a different density from what you can derive by a VHR satellite. But in any case, can identify specific area with an hotspot, with an alert that can be monitored with more detail thanks to the VHR satellite. We can measure the movement, but also effect on the building. In this case, we have the London Bridge, and there is identified in the red the movement derived by thermal dilatation. So it's not something due to a landslide or whatever, but within the structure, in this case historical structure, there is a dilatation due to the movement of car, due to climate effect, and we can monitor also this type of effect in the time. So it means that we can have a sort of indicator that can identify a possible issue. This is in Rome, the Palace of Justice. It seems that is everything. This is done by VHR satellite, like for the London Bridge. It seems that everything is stable, but if we are going to have a more detailed view, we can see that in the basement of the building there are identified movement, and this is a sort of indicator for the manager of the building that need to be activated a check by on field to understand what is happening. This is probably for this workshop the most relevant application is in Pompeii, in Casa dei Vetri, where there is an activities to the renovation work on this specific area with an installation of a roof, and we have identified, for sure is less relevant and less evident than the previous example, a sort of issue in this area. By a check made by ISPRA, this is an activities financed by the MIBACT, but also carry on with Leonardo and the ISPRA colleagues, that a beam of the roof have an issue, so need to be substituted, and is also to cover what is historical relevant and important. This type of application could be considered useful to support the management of a specific site. And this is the movement during monitoring during the time. This is another example also in the multi-risk. This is what we can do with the Cosmo SkyMed. This is again the INSAR. This is located in Sibari, again in south of Italy, where there is a very relevant archaeological site in this area. And we have identified with the INSAR analysis the ground stability. Ground stability means not only the structure, but also subsidence. So we have monitoring this by Cosmo SkyMed satellite. We have an alert on this area that there is a movement, for sure is in the delta of the river, so means different type of soil, and so it means different level of quantity of water. There is the salinity of the site. So there is something that are happening. We are seeing, and we have identified this area, and and this is what is derived by the INSAR analysis. But having experience on satellite data and having experience on data in general, our company have also derived by metadata and also through artificial intelligence the hydraulic model of this specific area, trying to understand a little bit more the causes of what are happening in this specific site. And so we have identified the water depth, so the level of the water, but also the velocity of the water in the specific area. And combining the two analyses, so not only the INSAR, but the INSAR plus the model derived by satellite data, but meteo data, and combining them, we have identified that what we have seen, this is on a port close to the archaeological site that is here, and fortunately we can see that up to now nothing happened in this specific area, was probably, because we have two analyses that combined identify this hot spot, causes derived by what happens when there is the flood of the river. So means that flood plus interferometric analysis are testimonying that there is the subsidence of the specific area. So I think that I have finished in time. So.
Thank you very much.
Thank you very much. So we move to the next presentation. I think it's on online contribution given by Monica Diaz, change monitoring over outdoor archaeological sites, Colonia, Clunasul, Spiša, Burgos, Spain.
Okay, good afternoon, everyone. Could you hear me?
Yes.
Yes, great. So let me just share my screen. Okay. So first of all, thanks ISA, and thanks to the organizers for inviting us. I just can be thankful about being a contributing mission ourselves. So my name is Monica Diaz. I'm responsible for products and services. And I will be just presenting some of the main capacities that we are providing to the monitoring of the cultural heritage from space. So really, I guess that everyone who just provide their insights about what could be the impact of Earth observation and in the monitoring and the preservation of the cultural heritage. So not only for the ecological sites, which are perhaps more exposed to climate change, but also some more recent monuments or historical buildings that perhaps it's also worth monitoring. You know that UNESCO has been just raised this climate action for World Heritage, just setting up climate change observatories and stating the best practices for monitoring, mitigation, and adaptation of those activities needed for the purpose. So in this case, what I would just like to stress or to highlight is the difference between different options that are available in the market in order to provide this monitoring of big areas, because obviously we are just having a widespread amount of cultural heritage along the whole world, and not only they are next to sites where people could just have a strict or periodic monitoring of their status. So just covering for large regions with scattered locations of those sites or cultural heritage locations are complex to tackle. So definitely we could just classify different type of data sources coming from aerial, from remote sensing, coming from satellites, either with very high resolution or let's say very high resolution coming from the well-known Sentinel-2. This is the main reference coming in currently in Copernicus. So obviously the characteristics are different. Resolution that could be achieved by drones or aircrafts are much higher than the ones that could be provided from resolutions, but also the revisit capacity that those satellites or the amount of area that could be covered with those options are much bigger. And not only this, but also the cost associated to wherever monitoring activities could be envisioned. Not only this, but also just considering applications of urban and infrastructure management, and also just monitoring the available status of the environment and available resources around that could affect as well those cultural heritage sites are critical and could definitely be best suited for the case of the area, but also for the very high resolution, since the detail that those images provides are quite relevant and quite comparable to those provided by aerial, but a much less cost. So regarding our company, we are just, as I said, contributing missions for ESA, for AirNet since 2015. And we are just featuring a full end-to-end control. We own and operate our own optical satellites. We have currently 2 in operations, which I can just confirm that perhaps one of them are one of the oldest missions being operated currently as a Copernicus contributing mission. It was launched back in 2009. With let's say not so big resolution because it's 20 meters, but really it has a very large swath of more than 600 kilometers, so the revisit it's quite proficient. But our main asset currently it's GeoSat-2, which allows to provide very high resolution with less than 1 meter up to 40 centimeter in fixed conditions. So it allows really to provide a service that could be tackled to whatever the customer application is. Being said that, obviously we are one of the 2 European providers of very high resolution imagery, and ESA is well aware of that, and we are providing services based on 24/7 operators, providing rapid tasking and rapid delivery with our more than 12 years of experience and a large archive available on our catalog. So with this background in mind, definitely we have experienced several use cases and different customer applications dealing with large coverages and the monitoring of large areas. Definitely, we consider that this large capacity could definitely complement wherever service could be provided by other type of data, such as the aerial, that could just perhaps provide more detail on the status of predefined sites, but also to SAR data, as our colleague from EIGEOS were presented. But the point here is that the monitoring being periodically available and having much more frequency than any other data could just have provides just a quick response, an early warning whenever an actual threat is considered as that could be applying to our specific sites due to whatever events, meteorological or human base could be provided. Not only this, but you know that with the latest news that we have experienced this week, the work or the activities in the space are just getting more frequent and therefore more experience and having less cost. So and having additional technologies being able to get apply over those data really provides a very sensible solution for any of the application that could be built upon the purpose of monitoring cultural heritage sites. Regarding optical data, as you can see, are quite thoroughly interpreted by photo interpretation, but only it is worth mentioning that automatic techniques could just also provide updates on the elements that we are just seeing, helping any investigator or any and not public servant could be just trying to extract information. You don't have to be an expert on treating with such kind of data in order to extract all the value from remote sensing. And that's an example. We can just ourselves at Geosat, we are just providing our own applications whenever tailored to whatever the customer needs are. And that's an example of how the monitoring of the elements around the different elements of different acquisitions at different stages of the year could just provide not only with new constructions or sport areas or under constructions areas that could just report what are the activities being held around a specific site, but also just providing a deeper classification on the type of elements that are checked. And this is an example that we have been carrying out, just trying to build up a general urban atlas that could just provide additional information on a large regions level. And not only a specific site that could just provide the detail, but the general rule that could help also to assess, to perform assessment at a larger scale. And just focusing now on the monitoring of archaeological sites, for sure GeoSat-2 data is capable of performing just this frequency monitoring that we were just mentioning in preserving and recovering the cultural and archaeological heritage. The very high resolution remote sensing can just definitely provide useful tools, but not only for the detention of the sites, but also for archaeological documentation and investigation. So these multi-source and multi-temporal imagery materials just definitely can guarantee a continuous monitoring of the state of the site conservation, and also provide different maps, AI-based modelings of the land use non-cover mapping at less than 1 meter resolution, which will definitely afford a solution to the surveillance activities being performed outdoor. Okay. So definitely that's a system that we could just pose an example that we carried out over an archaeological site. It was an old Roman city based in North Spain, in Burgos, and that's the rest of the elements that were visible and would be extracted, but these definitely were located within tons and tons of elements. So this the erosion coming through the years and the climate change definitely could just help to visualize whatever elements that could be still buried over large areas that perhaps could not be strictly visible at the human side from the but could be also seen from the space. So really, these automatic feature extractions for purposes could be feasible and really could provide complex textures and informations mainly by nodes and shadows on the imagery that could just detect changes or threats to the status or the evolution of the data itself or the sites itself. So that's just an example of what GeoSat-2 could just provide, and definitely we look forward to keeping our contributions to these solutions or these applications based on the preservation of the cultural heritage. So basically, that's pretty much what we have, and we'll be happy to provide you with any further information in case you have any question.
Thank you, Monica. Thank you for the presentation. Then, Mario will move. Yes.
Sorry, we don't have time for questions. Our next presentation is ESA Copernicus Sentinel expansion mission, and will be also a remote presentation by Anna Borsikowska.
Thank you very much. I hope you can hear me well. Can you confirm if you can hear me well?
Yes, we can hear you.
All right. So I'll put up a presentation. Thank you very much for inviting me for this session. Indeed, I was asked to talk about the Copernicus program and its evolution, and maybe also leading a little bit to the conclusion of your workshop, since we have very few presentations left. I think that we should be excited about the state of Earth observation in general, and I hope to excite you also about the future of Copernicus program, which does not probably need any introduction at this point, but in fact we should not forget about it at the time when we have such a wealth of data coming from commercial missions, and when we have many actors in private, public sector, military sector building new big Earth observation constellations. Why we should keep Copernicus in mind and actually consider this one of the key resource going forward and looking into the future, and that is primarily because this is in fact the most important asset that we have for both science and civil society, and this is primarily because of the free and open data policy which the Copernicus program plans to maintain for the years to come. Of course, you're completely aware that we are the primary source of data, Earth observation data globally, and ESA is tasked by the European Commission to ensure the seamless distribution of the data. And today, this is in fact taking place fundamentally through a new type of infrastructure that has been put together and operational since 2023, and that is Copernicus Data Space Ecosystem, which is, in short, basically the single entry point for all the users to download data, access data. In fact, this service is continuously evolving and introducing new types of capabilities. That includes, for example, a publication of monthly and yearly Sentinel-1 and Sentinel-2 mosaics. This is also the point where you can access all the VHR Copernicus contributing mission acquisitions, This is where you can also perform on-demand processing for all the Sentinel data archives and so on. So that is important to remember, that this kind of access point is being provided by ESA and in fact will grow in capacity. And it's today fundamentally filled with Sentinel or Copernicus first generation data, which are listed here that you know very well. The reason why I introduced this slide to this presentation is to say that actually we are going to have a very busy year in 2024 and 2025 and even 2026, where we plan to launch as much as 6 new Sentinel satellites into orbit, validate and bring them into operations. And that is the busiest launch schedule that any ESA program has today. And in fact, this is just a beginning, because by end of the decade, the size of the program will double. Because by around 2026, 2027, depending on the actual launch arrangements, the Sentinel expansion missions will be ready for launch. So that means that the program will move from the 6 family of missions to the family of 12 mission, which also means that we will have an exponential growth in data, the data volumes, but also data diversity. And when I say that this program grows from 6 to 12, it's not just a PowerPoint reality, so to speak. We are actually have a full funding and full agreement to build all these units to reality, and that means that the expansion missions are currently being built, and they are being built for both A and B units that will be in operations for the expansion missions program. So that is something to be very proud of, and this is something to be making a big difference by end of the decade for the entire Earth observation community. Now, these missions are relatively well known, I believe, in the community. So they are going to enhance and strengthen observational capabilities for climate change monitoring or climate change impacts monitoring, for food security, water management, and monitoring of land and natural resources. We also have 2 new missions coming online that will safeguard the Arctic and cryosphere monitoring. I'm not entirely sure that these missions, so Simmer and Crystal, if they are relevant to the cultural heritage community, but I'm betting that you might be interested in the capabilities of the missions which are dedicated to land and natural resources monitoring. So these would be the missions the 4 missions on the left side of this slide that I will focus on to tell you a little bit more about those forthcoming capabilities. So CO2M might not be directly relevant to cultural heritage, maybe except of the areas when you might be interested in studying the impact of environmental conditions on the deterioration of cultural heritage sites. But in general, this is ESA and Copernicus program truly flagship mission, because it's going to be the first mission that will be launched for the program, and this is the only mission that is currently considered to be built in the constellation of 3 units in order to ensure the daily monitoring of anthropogenic CO2 emissions. And this is not only the European first European CO2 mission, it's in fact first a global, truly operational carbon monitoring mission, which will provide the data on polluters monitoring, identification, and in fact pollution attribution. And it will have truly unprecedented swath resolution and precision. which will basically allow to provide the collocated monitoring of CO2 and NO2 emissions for the for the attribution to industrial pollution. Another mission which is also coming online and will be one of a kind capability given its technical specification is LSTM, which is Land Surface Temperature Monitoring Mission, primarily built to provide additional resources to monitor agriculture and water resources. It is being built to complement and enhance current observation of Sentinel-2 and Sentinel-3 with high spatial and temporal resolution. In fact, LSTM will have a resolution which is compatible with Sentinel-2 between 30 and 50 meters and very large swath, unprecedented swath of almost 700 kilometers, which will allow it to achieve a visit time of around 2 days. So here you have the animation that shows the actual mission observations plan. It will have 11 spectral bands, which will be collocated with, as I said, with Sentinel-2 and 3, and this large swath of 700 meters will allow to map a country of the size of Spain with just one satellite overpass. I hope the animations are displaying well. So here's the identification of the actual spectral bands that will be provided by LSTM. And complementary to LSTM, another mission in the Sentinel optical family is CHIME, which is Copernicus Hyperspectral Imaging Mission, which is in fact, let's say, a very multi-purpose mission which can be used for all kinds of applications for agriculture, monitoring to biodiversity management, environmental preservation, but also sustainable mining with the capacity to actually provide information, hyperspectral information on the geological formations. CHIME will be operating also in a 2-satellite unit constellation with a ground resolution of 30 meters and around 200 spectral bands, which is actually equivalent to 20 times, well, the collection capacity will be equivalent to 20 times the amount of data that is currently being collected by Sentinel-2. The primary priority application areas will focus on agriculture and food security, but as I mentioned also, this is going to be a groundbreaking mission for operational monitoring of soil properties, including soil texture, but also minerals detection and identification. And finally, on the land monitoring missions, Roselle, which is the first mission on using the L-band L-band capability, will be fundamentally providing additional observations to existing SAR missions. In particular, I will complement the Sentinel-1 with C-band, but also complement the numerous X-band missions which are coming online with in constellation concepts. So this will, of course, allow to map and improve disaster mitigation, earthquakes, landslide, volcanoes, flood monitoring, and so on, but also maybe interestingly for your community to provide additional mapping under canopy and provide additional temporal variations of soil moisture and crop types. All these missions are currently being prepared for operational exploitation under the Sentinel User Preparation Program, which is also developed currently at ESA with some number of projects being tendered and developed in order to prototype first data products and prepare synthetic data in order to prepare the user community for data exploitation. And on top of this, I want to mention also the current planning for the extension missions. So so Copernicus Sentinel extension missions are the Sentinel's next generation, which will replace the current generation. So we are looking into the missions which will follow on Sentinel-1, 2, 3, and 6. These missions are currently being prepared under ESA Copernicus Space Segment Program, and some of them are actually already entered the development phase, some of them are in the study phase. But here you can also understand a little bit better of what kinds of enhancement in the capabilities or observation continuation we are looking at. So for example, for Sentinel-1, it is not only going to focus on increase in resolution from 10 to 5 meters, but also, for example, introduction of full polarimetric capabilities considered, and leading to a multi-SAR constellation, multi-frequency SAR constellation combining Sentinel-1, Roselle, and CSAT mission, for example, for marine applications. The same is considered for Sentinel-2 next generation, which is currently considering a better resolution, so doubling the resolution from 10 to 5 meters, doubling the number of spectral bands, and the mission is designed to have much better synergy with Sentinel-3, LSTM, CHIME, and Landsat. And so on. I won't go through all these missions descriptions. As I said, they are actually in the some of them, majority of them, are in the study phase. But what I want to focus on as a final word is to say that these missions are in fact being built and prepared to be much more compatible with constellations or multi-mission constellation concepts. And on the one hand, we are looking into hybrid constellations to understand and to study how commercial complementary capabilities can be introduced to the Copernicus program. Copernicus contributing missions is a first step to provide this kind of technological feasibility for these missions. But in reality, the availability of commercial sensors will enhance the Copernicus agility and fill the observational gaps. And this has been identified as one of the key objectives for the forthcoming multilateral financial framework of the European Commission, to double or even triple the budget for the Copernicus contributing missions in order to bring in more of those assets in hybrid constellation concepts architectures. And finally, I will leave you with this illustrations of the synergy between or planned synergy between different missions, which is what the Copernicus program plans to achieve by end of the decade. And it also shows that this mission synergy will provide a completely unprecedented coverage with completely unprecedented data diversity from around 2028 onwards. So thank you very much.
Thank you, Anna. Unfortunately, we don't have time for questions, but thank you very much.
So we move to the next presentation. José Manuel Delgado Blasco will have a presentation about the ESA Incubed program.
For the brave attendants. We are heading now to the very last presentation of the conference. So I want to talk about the ESA Incubed program. So it's investing in industrial innovation. And I will put some focus on for the preservation, monitoring, and enhancement of the cultural heritage. So in the ESA IOP commercialization had several roles. And so we have, for example, ESA IOP as an enabler, which they are having fully funded projects in which they can enabling downstream applications, commercialization, also upstream technology with different blocks. We have SIOP as a partner, so InCube, which are co-founded industry-led program. That means that is industry proposing their own ideas to be developed. Then we have as well SIOP as a customer. It is linked to the Copernicus Contribution Mission and the TPM we said before, that they are buying data for themselves or also for third-party partners. So yeah, this is us. So we'll talk about a bit more about it. I mean, you heard about InCube several times in the last 2 days, also early this morning. Sorry. So well, we have a fund size about more than 200 millions, more than 140 activities and still rising. And the funding average goes for a few hundred thousand euros to more than 15 million euros, depending on the activities, size, scheme, whether the scope, and so on. So in the program, we give personalized technical and commercial guidance. It is a zero equity and zero IPR, so whatever is produced, the IPR is for the industry. They have obviously is a stamp of credibility after the project ending, and they also get a privileged access to commercial services and enabling development, and access to ESA fill-up. So what actually InCube is? So we are the industry-led, as I said before, commercial program with focus of developing Earth observation derived products, services, hardware and software, but with a focus on commercially successful products. So our scope is actually that the products are really to be sold directly after the final project, and it has to be credible. So they need to be with a business case, credibility, and if possible with some engagement of stakeholders or somebody that would like to do the pilot demonstration of the products. So it is a permanent open call, so you don't need to wait for any quarter or any time. Anytime you have your idea, you can submit there. Yeah, and then describe what you want to do. It should be technically feasible, so we will assess that. It should be Earth observation related, obviously. So we are here in ESRIN, so it needs to be Earth observation linked. And it is a program in which industry, ESA, and national delegations will work together. So we need to collaborate to bring this forward. So this is a bit the schema of what is the process and so on. So just to show that you have 2 entry points to our program. So basically, depending on the outcome of the TRL, so if what you are proposing, it is not yet to be sold, you may adopt the de-risking cycle, for which the outcome should be like already consolidated requirements, already consolidated business case, and then if it can be applied for a CCN and go to the product development phase, for which the output should be directly a commercial oriented product service. It could be upstream, downstream. Here there are some numbers, but I would like just to focus, you take your attention to the co-funding level, which depends on the company size, but also can be in the consortium included academia and researchers. That maybe is more interesting for yourself, because I believe most of the people here still from research institutes and universities. So yeah, in that case, they can get up to 100% of co-funding, but they should not have any interest in the commercialization of the final product. So yeah, I will be quite fast. So here, yeah, I mean, what do we offer? So we offer a risk sharing, because obviously if you are proposing innovative products or services or satellites, there is a risk on there. So it can be a technological risk or a business case risk. So we share that with equity and APR-free co-funding. So this is what is more attractive, because if somebody wants to develop their own new services, and they may have some risk that they would like to share with us. So we also give personalized technical and commercial guidance. So we have a large team of expertise here to support these kind of activities, also satellite developments, sensors, also with collaboration with the team of ESTEC. And we also have, obviously, a strong connection with the private investors in coordination with the Directorate of Commercialization, Industry, and Competitiveness. So yeah, just to show some of the names of the companies we have supported upstream. There are many of them could be also familiar to you. Some of them they were already mentioned before, in which 5 of them were already awarded with a contract with the CCM, which they were mentioned before, and for the new space companies with offering really new and innovative sensors and visit times constellations. And then we also have, there's not exhaustive list, it's just some of them. We also have some downstream companies. I mean, you better not get surprised if it is a large company or a small company or a startup. So all of them are more than welcome. They will have different things to propose, different idea, different co-funding scheme. But all of them are welcome to the program as far as they want to develop something with Earth observation related. So yes, here, just to put a map in the timeline as well for the satellites that need to be launched. Some of them are a bit delayed until now, so they will be basically launched in 2025. So we see the Aurora Tech, Hive, IX from Planetech as well, and the other ones there are still under development. So yeah, I will try if this works. Yeah, okay. As being a commercialization program, we want also the projects to be clear where the markets they want to target, which user segment, which applications, which are the risks, which are the forecasts. So for example, we saw that just getting some reports on the Earth observation market, we see a growth that it will double in the next 10 years, in which obviously the cultural heritage segment can take part also on urban planning, and to be sure that the UNESCO cultural heritage sites are not really having under pressure for the urban developments nearby. We saw the cases of Giza Pyramid Garden, for example, and many other ones around the world. They may have as well for air quality monitoring, water monitoring, depending if it is a natural site, natural cultural site as well, or any other ones. There are many other applications we've seen also in the last 2 days, for which if they want to develop something new for a company or something new in the market, they should know whether they may have a place in the market to fit. So it should be, as I said, a credible business case. So they will, because at the end they want to commercialize it and get money from it. So in Cube itself, we had last year an open call campaign dedicated for archaeology. That doesn't mean that it wasn't an open call, a permanent open call. Yes, we are a permanent open call, but sometimes we release also specific call dedicated to, in this case, archaeology, infrastructure, or any other one that could come. We have currently, if you remember the first presentation of today, it was a Smart Dig presentation. They have also the letter of support of the Italian Ministry of Culture, but we have also some other projects that are still not formalized, in which is disappearing. So it's something that is new, to have them expressing their interest in the products that the market is developing for their own marketing purposes. But again, a part of these specific activities that they have been focused on archaeology or activities for preventing archaeology in this case, we have many other ones, activities that are being developed that can be also used for archaeological purposes or cultural heritage purposes. In case they are natural or not, they can be monitoring of the environment, so water, air pollution, or land use, land cover changes, or any other one. We also see that they have other activities that they develop specific monitoring platforms for analyzing as well stability of the assets. So we saw as well these days many INSAR applications that they can give really insights and detail on large infrastructures. But we also have this kind of activities supporting within InCube. Also for climate-related risk assessments and other ones. So just to name a few of the activities we have, some of them directly related to archaeology, other ones related to the development of sensors, satellites that can increase the revisit time. Some presentation before they were saying that the spatial resolution or the temporal resolution is many times an issue for depending on the activities you want to carry on. So here we are also developing this kind of new constellations with new sensors with very high resolution that had not been before. Also other ones that can be for environmental purposes or risk or infrastructure risk assessment and so on. So yeah, with this, you want to take just a look, which are the companies, which are the full activity portfolio, just visit the website. I invite you to do so. And with this, I end my presentation. So thank you very much. If you have any question, I will be here later.
We don't have time for questions, sorry.
Distinguished guests, my apologies for the technical problems earlier today, and I hope that through this video message I'm able to join you and bring to you the what we had planned to discuss and bring to you this morning. So I wanted to first of all thank the European Space Agency and the European Association of Remote Sensing Laboratories for organizing this very important workshop. And I'm very happy to be here on behalf of UNESCO and to bring some of our work on Earth observation and heritage conservation to the discussion. More than 50 years ago, there were two parallel events, and I want to share my screen now. So let me see if I can share my screen. I think you should be seeing my screen now. So the two parallel events that happened, more than 50 years ago was to do with the, on the one hand, the initiation of routine Earth observation via satellite with the launch of Landsat 1, and the landmark and groundbreaking event equally significant of the 1972 World Heritage Convention being adopted. So what we are now, we are more than 50 years past this landmark, and the convergence of heritage protection and space technology is, of course, only more important today than it was before. And we're looking also at contemporary global challenges such as climate change and disasters from natural hazards, urbanization, pollution, a number of other things that require and could use Earth observation. So the first. Well, I might say that while spatial information through aerial photographs has been broadly used in heritage management for a number of years, the first application was in the 1990s. And in Central America, for instance, Earth observation and satellites enabled us to look at better understand Mayan civilization. And the technology has given archaeologists a way to see Mayan civilization as water use and the transition between the Maya periods. Satellite data has helped to explain Mayan water use and the sudden migration that occurred due to a sudden lack of fresh water. In another example involving cultural heritage sites, the sprawling complex of Angkor in Cambodia was mapped in the late 1990s using radar imaging. And high-resolution data from the Copernicus program, a private sector satellite imagery drone, offered unprecedented accuracy, allowing us to monitor sites remotely in techniques like LIDAR and 3D modeling that supported more robust conservation strategies. In 2001, UNESCO launched the Open Initiative on the Use of Space Technologies in UNESCO sites, encouraging international space agencies to support developing countries in monitoring their World Heritage sites. This initiative brought together key actors like the European Space Agency, the German Aerospace Center, and the Belgian Science Policy Office, among others. Under this initiative, projects were carried out to map remote World Heritage sites in places like Central America and Central Africa. In 2011, the International Center on Space Technologies for Natural and Cultural Heritage, or HIST, was established as a UNESCO Category 2 center, hosted by the Center for Earth Observation and Digital Earth, the CIOD, in China. And HIST has provided key information to monitor the serial site Silk Roads in China, Kazakhstan, Kyrgyzstan, as well as in Jiuzhagu Valley Scenic and Historic Interest Area in the Sichuan province in China after the 2017 earthquake. Since 2015, UNESCO has partnered with operational satellite application programs and the UN Institute for Training and with the UNITAR UNOSAT to assess damage and cultural heritage in emergencies. We have conducted assessments in Iraq, Libya, Mali, Nepal, Yemen, Syria, just to name a few. And one significant project was the detailed analysis of the damage in Aleppo's ancient city during the Syrian conflict. This resulted in a comprehensive report that now helps prioritize recovery efforts. And today, UNESCO continues to assess damage in conflict zones, including in Ukraine and Gaza. In 2021, UNESCO joined forces with the Group on Earth Observation GEO and the Greek Geo Office to establish the Urban Heritage Climate Observatory to use Earth observation tools and methods for climate modeling, monitoring, and solutions for World Heritage cities. A current study is now being carried out for looking at the Mediterranean region using both state party reporting as well as climate modeling and Earth observation to understand and project likely climate change risks to World Heritage cities in the Mediterranean. An example that shows how satellite data can be used to undertake global studies for World Heritage sites are the World Heritage Forest Carbon Sinks Under Pressure and World Heritage Glaciers Sentinels of Climate Change report that we launched together with IUCN in October 2021 and November 2022. The forest report was the first global scientific assessment of greenhouse gas emissions and sequestration by forests in UNESCO World Heritage sites, and the baseline for such a study was tree cover satellite data. The study revealed that every year World Heritage forests absorb 190 metric tons of CO2, equivalent to half of UK's annual fossil fuel emissions, but that alarmingly, some sites have been carbon sources as a result of climate-related events such as wildfires. The Glacier Report was the first global scientific assessment of glacier retreat in World Heritage sites and has shown that every year World Heritage glaciers lose 58 billion tons of ice, equivalent to the total annual volume of water consumed in France and Spain together, and contribute to almost 5% of global observed sea level rise. It is very important to stress that it's crucial to make sure that the information from satellites can go all the way to end users and site managers and be readily accessible to them. In this regard, we are also cooperating with the European Union Joint Research Centre through the Copernicus Programme and the Digital Observatory for Protected Areas, DOPA. Climate change is now among the top threats to cultural and natural heritage sites inscribed on UNESCO's World Heritage List. In the past few years, we've seen an increase in the number of sites being affected by weather-induced disasters, and climate change reports on state of conservation of World Heritage sites that indicate that all types of World Heritage sites are vulnerable to impacts of climate change in all regions of the world. Furthermore, it's important to mention the situation of World Heritage cities, as the climate crisis is particularly critical in cities where half of the world's population resides. I want to move now to talk about addressing the gaps in capacity and capacity building and resources. Despite these advancements and several challenges remain, many World Heritage sites lack the resources and capacity to monitor climate-related risks affecting more than 1,000 sites as of today. We do not have a comprehensive assessment of how many sites are threatened by climate change and weather-related hazards. This is particularly true for cultural sites, and Earth observation offers a way to bridge these gaps by providing real-time and detailed monitoring. To support the same and in the spirit of UNESCO recommendation on open science, UNESCO launched the World Heritage Map Online, which platform last year, as well as the UNESCO Urban Heritage Atlas, which is aimed at making spatial information on UNESCO designated sites accessible to all. The World Heritage Map Online platform is an online GIS monitoring tool for World Heritage, displaying georeference boundaries of World Heritage sites and their buffer zones. This platform has been made available thanks to the generous support of the government of Flanders and Belgium, and has been public since 2023. This platform is just the beginning of systematically integrating Earth observation and remote sensing technologies into heritage management. Through all the World Heritage Online Map platform, the UNESCO World Heritage Centre aims to provide states parties as well as heritage and non-heritage stakeholders with an online cartographic tool for improved monitoring of the state of conservation of World Heritage properties. This platform constitutes a first step at the Centre to harness Earth observation and remote sensing for heritage preservation, and as the first time that the Centre has started to work systematically with geospatial data and produce a geospatial database of site boundaries as adopted by the World Heritage Committee. And this is an example of 33 World Heritage properties, including extensive coral reefs, as part of the attributes conveying the outstanding universal value of these sites, where many reefs are threatened by ocean temperatures that are increasingly becoming warmer than the coral animals' natural tolerance. When water is too warm, corals expel the algae living in their tissues, causing the coral to turn completely white. And this is coral bleaching. So the satellite data provides the reef conditions, including for World Heritage sites. This is another tool, which is the UNESCO Urban Heritage Atlas. As I said, the World Heritage Cities are today more than 300 World Heritage Cities inscribed on the World Heritage List. This is both an atlas and an archive that is visually, narratively, and through analytical maps, documents, explains the diversity and uniqueness of World Heritage, the world's historic cities and settlements. And as such, it helps to preserve our heritage, document it rather, and helps also to contribute for its management. Historic cities are repositories of city building practices and are across diverse regions over time. So it also includes, this platform includes vernacular architecture and traditional building techniques. While many collections and publications on World Heritage Cities have been produced over the years, the diverse dimensions of World Heritage properties in urban contexts remain inadequately understood, excuse me, and is often not managed in isolation of the urban dynamics. So the Atlas fills this gap by providing interactive mapping of urban fabrics and settlements of having the heritage characteristics, looking at it at 4 different levels. A level of the historic building on the scale, the second is looking at the urban elements, and the third is looking at the wider setting of the urban area, and finally the intangible heritage dimensions, in order to look at how each of these as characteristics and the attributes at each of these scales can be preserved and managed. And today the platform hosts 10 case studies from different countries with plans to expand continuously. On its landing page, the platform explains its role as an atlas and its technical capabilities and its function excuse me, as a cultural mapping tool and learning resource. And we currently have 10 case studies online, or of these urban studies, representing various regions of the world, and the UNESCO Urban Heritage Atlas helps to identify and map, visually present these. And so while it is something that can be implemented in all cities, all historic cities, at the moment we are focusing particularly on World Heritage cities. So there's interactive mapping at these 4 scales that I mentioned, from the building level to, and you can see these noted very clearly in the mapping. That is based on a GIS map, where you can see in the legend the different, and these are different examples of cities, but you can see the attributes of the wider setting, the attributes of urban elements, and the historic building attributes very clearly listed here. And you see the neighborhoods also at different scales. So by the end of this workshop, we hope to enhance our understanding of how Earth observation technologies can be more widely adopted in heritage conservation and preservation, and encourage everyone to contribute actively and share best practices, as the future of heritage preservation depends on our ability to harness the power of space technology effectively. I wish you all success with this event, and thank you for your attention. And I also want to express my gratitude to the European Space Agency and the EARSEL for organizing this event. For more information, you may also be interested to look at the issue number 98 of World Heritage, dedicated to the use of space technologies for heritage management. So with that, I thank you all very much. Thank you and goodbye.
So I guess we are closing the workshop now. We actually have a few slides with very few concepts. You have been very brave, and there are also some brave ones online. So if you can just project our conclusion, then we will go a bit faster. I know taxis are outside, so yeah. I'm waiting for the slides.
You want to change?
Yes, so thank you. I will start from the end. So thank you for coming and attending. This is just a quick recap of what we have seen in these 2 days. These are our 4 sessions, so just for overview of what we were going through. These are not written into stone, so we can also adapting them to new needs in our next events. This is the audience, so were you and who was attending the conference. We had a lot of experts from the Earth observation sector, archaeology and cultural heritage as well, educational, private, public sector. So I would say a good representation of audience. And this is me when I was still an archaeologist and without any space in my life. Concerning the data and the techniques, so this is an overview of what we have seen. So LiDAR, cartography, UAVs, historical acquisitions. We have ground sensors and, of course, Earth observation data sets. In terms of imagery, Earth observation imagery, we have seen many examples from SAR and optical data. And concerning techniques, we went through the exploitation of SAR and optical dataset, the backscattering analysis, the infrared and microdoppler, hyperspectral, change detection, and machine learning and artificial intelligence as well. Just a quick insight into a bit more technical discussion. So as we have seen, we also had some presentation about Sentinel-1 applications. And this is just for letting you know that with the expansion of the missions, of the ESA missions, we will get also something which is very important in the cultural heritage sector, which is the very high resolution we are missing since decades. So is still something nice to come. And in terms of applications, so we had all the climate change effects and the looting, the lab grabbing, pollutants, tourism management. We have seen also some examples coming from the preventive archaeology and some other specific techniques coming from the space sector, but actually applied to the cultural heritage, the muon topography or the presentation that we had also today. And I think I'm concluding this first section very quickly, saying that we understood from this workshop, apart from that we don't have time for questions, but also that we need to take to remind that we have a knowledge gap we need to address in our future activities, and this is on both directions. So Earth observation people should go a bit more closer to the cultural heritage experts, and cultural heritage should be a bit more closer to the remote sensing experts. So I think now I will leave the floor to my colleague.
Thank you, Yolanda. So what we observe in the workshop as progress done, so archaeologists are using Earth observation. In the sense, not only satellite data, but remote sensing in general with drones, with all the tools. There are starting to be services available. And so we can take advantage of land cover change, heritage risk, and the private sector is getting involved. So they are clever people, and if they are getting involved, they are seeing a business, so they are seeing that this is consolidating. But still, we're mainly among the EO community here. So something we need to do in order to attract the heritage community. And yesterday, discussing with Gordon Campbell, he said we need to attract the tourist authorities because they are earning lots of money. They are using the sites, they are damaging the sites, so they should be involved in the conservation or in understanding that these techniques are useful. There are lots of opportunities. We need to jump into the opportunity. So ESA is proposing to have this workshop each 2 years with the help of Yolanda, so that's quite good. As Jose Maria Blasco presented, there are some small funding opportunities, so I think we should also try to take advantage of that. And some of the participants are dealing with developing educational material for Earth observation and heritage, so I think we can help because that will attract more than educational material. I see as awareness material, which is needed. For consideration, for example, we could select a heritage site, the preference an historic city in order not to be in archaeology all the time, that the Heritage Authority help us defining what is the cultural landscape, so which is the whole area of interest. And then when I was teaching remote sensing, if I wanted to show to non-remote sensing people the resolution of satellites, I needed to jump all over. So here you have Paris at 80 meters, here you have New York at 4 meters resolution. So why not for a single site like this one, then to have images of all possible resolutions, the legacy and the new ones, so that we can show what it means to be at 80 meters resolution, what it means 30 centimeters resolution. Then we saw SAR ascending and descending, but for the same site, and for the same site, obtain SAR 3D model. And then big data management, see how we can involve the artificial intelligence, see what each this discipline can cooperate. And then we have visualization and all the new tools, digital immersion, digital virtual tours, and gaming. Gaming is not for children. Gaming are becoming very sophisticated, and we can create lots of awareness with gaming. We saw it in the presentation that we had today. It's already very nice games that can be done there. As announcement, we're going to have the Ursel Symposium in Prague from 26 to 29 May. There is a special session on heritage. If we have enough response, we can have then a workshop inside the symposium. Or if not, a session. So please consider sending an abstract when the announcement is there, and we hope to see you there also. And ESA is having the Living Planet Symposium. Is a very interesting event. Is the whole of the European space sector is there. It's in Vienna in June. And there will be an agora that will be announced on Earth observation for heritage. And so that's also something that you could consider. And finally, in December, we have the GRSG annual conference of ESRI.
Yes, this is a typo. It's this year, so it's 2024, and this is the Geological Remote Sensing Group. So many applications actually are using the same technologies, and what we can do in cultural heritage can also be done in other domains. So it could be also interesting for the ones that want to participate to get this. This year, yes, it's this year. Yeah, this is a typo. It's 2024.
And so finally, Yolanda and myself, we would like to thank you for responding to this call, for being here. When we were reviewing the papers, we decided to include as much as possible, and that has made us to go very quick, but we have seen the whole spectrum of what is possible. So I think it worked out as a good strategy. And so please share your feedback about the workshop, and have a safe trip back, and enjoy the evening in Frascati for those that are still remaining here.
Thank you.
Congratulations, it went very well. Yes. I know it was very hectic for you. So when are you going back to
I'm flying on Friday.
Nice to meet you.
Nice to meet you. Nice to meet you. Yeah, see you soon.
To meet you.
Ciao, grazie, ci sentiamo, va bene, grazie. Sure, Mario. Then let me kiss you. So Thank you. Thank you so much.